What is nothing? It's a question that seems simple but has puzzled thinkers for centuries. Is it a void, an empty space, or something more mysterious? Philosophers have debated its meaning, scientists have studied its properties, and artists have tried to capture its essence. Join us as we'll explore the concept of nothing. The universe is the grand stage of existence, an expanse that encompasses all of space and time, the very fabric in which galaxies, stars, and planets find themselves situated. Estimations suggest that the observable universe stretches over 93 billion light-years in diameter. Perhaps even more mind-boggling than its size is its age, around 13.8 billion years. This immense realm contains an approximated 2 trillion galaxies, each harboring millions or even billions of stars. But the universe isn't just a collection of celestial bodies, it's a symphony of particles and forces, a constantly evolving entity governed by the laws of physics. Scientific theories like the Big Bang model offer insights into the universe's origins, positing that it began as a singularity, an infinitely dense point, and has been expanding ever since. Dark matter and dark energy, though not directly observable, are believed to make up about 85% of the universe's mass and influence its expansion and structure. As we gaze into the cosmos with ever more sophisticated telescopes and instruments, we continue to unravel the astonishing complexities hidden within this boundless expanse, deepening our understanding of what the universe truly is. The vastness of the universe defies comprehension, stretching the limits of our imagination and understanding. To paint a picture, the observable universe extends 93 billion light-years in diameter. In other words, light, which travels at an astounding speed of about 186,000 miles per second, would still take 93 billion years to traverse the observable cosmos from one end to the other. This enormous expanse hosts an estimated number of galaxies that stands at 2 trillion, each galaxy housing billions of stars and potentially even more planets. Our own Milky Way galaxy, a relatively standard spiral galaxy, contains about 100 billion stars. Yet the limit of the observable universe does not imply a boundary. Rather, it's the furthest distance from which light has had time to reach us since the Big Bang. Beyond this observable limit, there may be much more of the universe that remains unseen, and perhaps for now, unknowable. This immense scale challenges not just our scientific instruments, but also our philosophical perceptions of our place in the cosmos. It makes the realization sink in that, within this mind-boggling immensity, our Earth is but a mere speck, a tiny fragment drifting through a timeless and boundless ocean of space. The observable universe refers to the portion of the entire universe that we can see and study with the aid of our current technology and scientific methods. It's a concept bounded not by physical walls, but by the limits imposed by the speed of light and the age of the universe. Given that the universe is about 13.8 billion years old, the furthest distance light has traveled to reach us is also approximately 13.8 billion years. However, due to the ongoing expansion of the universe, the actual distance to the edge of the observable universe is around 46 billion light-years in every direction, cumulatively resulting in a diameter of about 93 billion light-years. This observable cosmos contains an immense variety of astronomical phenomena, from sparkling galaxies and star clusters to enigmatic black holes and glimmering nebulae. Despite the observable universe's overwhelming expanse, it might represent only a fraction of the total universe, which some cosmological models suggest is far larger, possibly even infinite. Scientists use tools like the Hubble Space Telescope and the recently launched James Webb Space Telescope to probe as deeply as possible into this vastness, capturing light that has traveled for billions of years to give us glimpses of distant corners of the cosmos. While limited by the speed of light and the universe's age, the observable universe offers a profound window into the history, structure, and evolution of the cosmos. Measuring the size of the universe is an endeavor that combines cutting-edge technology with sophisticated scientific theories. At the heart of this measurement is the speed of light, which acts as a cosmic ruler. Light travels at approximately 186,000 miles per second, and by observing light from distant celestial objects, we can measure how far it has traveled over billions of years. This forms the basis for determining distances within the observable universe. One of the principal tools used by scientists is redshift, the phenomenon where the light from distant galaxies shifts toward the red end of the spectrum due to the expansion of the universe. The further away a galaxy is, the more its light is redshifted. This relationship, known as Hubble's law, allows scientists to calculate the distance to far-off galaxies. Coupled with advanced instruments like the Hubble Space Telescope and the newer James Webb Space Telescope, astronomers can measure these distances with unprecedented accuracy. Additionally, other methods such as observing Type Ia supernovae, stellar explosions with a known intrinsic brightness, serve as standard candles to measure astronomical distances. Cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the early universe and helps refine estimates of its size and age. Through these approaches, scientists have deduced that the observable universe spans about 93 billion light-years in diameter. However, the ultimate size of the entire universe, beyond the observable part, remains an intriguing and open question, potentially extending infinitely or existing as part of a larger multiverse. The universe is a grand tapestry woven with a myriad of components, each contributing to its intricate structure and dynamic nature. At the broadest level, the universe is composed of massive galaxies, vast assemblies of stars, planets, gas, dust, and dark matter, all bound together by gravity. There are an estimated 2 trillion galaxies in the observable universe, ranging from tiny dwarf galaxies to colossal giants. Our own Milky Way is a spiral galaxy, home to around 100 billion stars. Stars are the luminous engines of the cosmos, undergoing nuclear fusion to produce light and heat. These stars can vary immensely from smaller red dwarfs to massive blue giants and supergiants. Some stars end their lives in spectacular explosions called supernovae, giving birth to neutron stars or black holes. The remnants of these explosions enrich the surrounding space with heavier elements, facilitating the formation of new stars and planetary systems. Planets, often orbiting around stars, come in diverse forms and sizes, from rocky terrestrial planets like Earth and Mars to gas giants like Jupiter and Saturn. Some systems even have exoplanets, planets orbiting stars beyond our solar system. Additionally, smaller celestial objects like moons, asteroids, and comets add to the complexity of stellar systems. Interspersed within and between galaxies is interstellar and intergalactic space, teeming with gas and dust, the raw materials for star formation. Dark matter, although invisible and only detectable through its gravitational effects, accounts for roughly 85% of the universe's mass. Even more mysterious is dark energy, a force thought to drive the accelerated expansion of the universe, making up about 68% of its total energy content. Together, these components create a universe of extraordinary diversity and complexity, offering endless avenues for exploration and discovery. Defining nothing in the context of the universe's origin is a concept that stretches the boundaries of both scientific understanding and philosophical contemplation. In everyday language, nothing might imply a complete absence of everything: matter, energy, even space and time. However, when it comes to cosmology, the notion of nothing becomes more nuanced and complex. Before the Big Bang, which marks the beginning of our universe approximately 13.8 billion years ago, there wasn't just an empty void. Even the fabric of space and time itself did not exist. One way scientists attempt to conceptualize this nothing is through the lens of quantum mechanics and the vacuum state. In quantum theory, even a perfect vacuum isn't truly empty. It seethes with temporary particle-antiparticle pairs that pop in and out of existence, a phenomenon known as quantum fluctuations. In this sense, nothing could be described as a state devoid of matter and classical energy, but still pregnant with potentiality and the underlying quantum fields that enable these fluctuations. Some cosmological models suggest that the universe could have emerged from such a quantum vacuum state due to these fluctuations. Another approach is through the framework of general relativity, where the curvature of space-time depends on energy and mass. If no mass-energy exists, space-time as we understand it ceases to exist as well. In this context, nothing could mean a state where space and time are undefined. The transition from this nothingness to the universe's birth remains one of the most profound mysteries that science is striving to unravel. Thus, while nothing in the cosmological sense isn't simply an empty void, It signifies a profound absence of the structures and forces that came into being with the birth of the universe. The question of the universe's origin is a profound one, captivating the curiosity of humanity across cultures, disciplines, and eras. Delving into this question isn't simply an academic exercise. It forms the cornerstone of our quest to understand the nature of existence itself. Exploring the beginnings of the universe helps us grasp the fundamental laws of physics, forging connections between the macroscopic worlds of galaxies and the microscopic realms of quantum mechanics. By understanding the universe's origin, we gain insights into the fundamental forces that shape reality, including gravity, electromagnetism, and the nuclear forces, shedding light on how matter, energy, space, and time came into being. Moreover, pondering the universe's inception provokes existential reflections, tapping into our innate desire to comprehend our place in the grand scheme of things. Scientific theories about the universe's origin, from the Big Bang to cosmic inflation, challenge and expand our worldviews, prompting us to rethink concepts of time, space, and existence. This inquiry also fuels technological advancements and scientific breakthroughs. The quest to understand the early universe drives innovations in fields ranging from astronomy to particle physics, leading to the development of cutting-edge telescopes and particle accelerators. Thus, seeking answers to the universe's origin is not only about tracing the cosmic timeline, but also about pushing the boundaries of human knowledge and inspiration. Ancient civilizations, long before the advent of modern science, crafted intricate and imaginative narratives to explain the origin of the universe. These creation myths not only provided a framework for understanding the cosmos, but also imbued it with cultural, spiritual, and moral significance. In ancient Mesopotamia, for instance, the Babylonian creation epic, the Enuma Elish, tells the story of how the god Marduk defeated the primordial sea goddess Tiamat and used her body to create the heavens and the earth. This myth intertwined the origins of the cosmos with themes of order triumphing over chaos. In ancient Egypt, creation myths often centered on the god Atum, who emerged from the chaotic waters of Nun to form the world. Atum was believed to have created himself and then produced the gods Shu and Tefnut, who in turn gave birth to Geb, earth, and Nut, sky, establishing the basic components of the universe. These stories provided ancient Egyptians with a sense of continuity and divine order in their environment. The ancient Greeks offered a variety of narratives, with Hesiod's Theogony being one of the most influential. According to Hesiod, the universe began with chaos, a void or nothingness, from which emerged Gaia, earth, Tartarus, the underworld, and Eros, desire. These primordial entities gave rise to the gods and the physical world. The Greek myths often emphasized the gods' roles in shaping the universe and human destiny, reflecting the Greeks' views on power, morality, and the natural order. Similarly, in Hindu cosmology, the Rigveda describes a universe that emerged from a cosmic egg, Hiranyagarbha, and underwent cycles of creation, preservation, and destruction involving gods like Brahma, Vishnu, and Shiva. These cycles, known as yugas, illustrate a universe in constant flux, governed by divine will and cosmic laws. These ancient explanations were deeply embedded in the cultures and religious practices of their respective societies. They provided not only cosmological insights, but also ethical guidelines, social structures, and a sense of identity and purpose for the people. While these myths differ widely in their specifics, they share a common goal: to elucidate the mysteries of the universe and humanity's place within it, weaving together the known and the unknown into narratives that could be passed down through generations. The creation of the universe has been the subject of countless mythological stories across different cultures, each imbued with its own unique symbolism, deities, and cosmic events. These stories serve as windows into the worldviews and values of the civilizations from which they originated. Norse mythology, the creation of the universe, involves a dramatic clash between primordial forces. According to the Prose Edda, the cosmos began with a yawning void called Ginnungagap, flanked by Niflheim, a realm of ice and mist, and Muspelheim, a land of fire. When the ice and fire met in Ginnungagap, they created Ymir, a giant, and Audhumla, a great cow whose milk nourished Ymir, From Ymir's body, the gods Odin, Vili, and Ve fashioned the world. His flesh became the earth, his blood the oceans, and his bones the mountains. The sky was formed from his skull, and his eyebrows created Midgard, the domain of humans. In Chinese mythology, one of the most famous creation stories is that of Pangu. According to this myth, the universe was originally an egg containing chaos and the opposing forces of yin and yang. Pangu, a giant, emerged from the egg, separating yin from yang with his strength. As he grew, he pushed the sky upward and the earth downward, creating the world. Upon his death, his body transformed into various elements of the natural world. His breath became the wind, his voice thunder, his eyes the sun and moon, his body the mountains, and his blood the rivers. The Maori of New Zealand have their own account of the creation called the separation of Rangi and Papa. In this myth, the Sky Father Rangi and the Earth Mother Papa were locked in a tight embrace, leaving their children, the gods, confined in darkness. The gods conspired to separate their parents to bring light to the world. After many attempts, the god Tanemahuta succeeded in prying them apart, with Rangi becoming the sky above and Papa the earth below, thus creating the world and making space for all living things. These stories, while diverse in their details and characters, often share common themes: the struggle between order and chaos, the transformation of primordial entities into the physical world, and the involvement of divine beings in shaping the cosmos. They illustrate how ancient cultures sought to make sense of the existence and structure of the universe, grounding their understanding of reality in rich narrative traditions that have been passed down through generations. Early philosophers and scientists laid the groundwork for our contemporary understanding of the universe by transitioning from mythological explanations to more rational and observational approaches. Their views on the universe were deeply influenced by their observations, philosophical frameworks, and the limitations of their times. In ancient Greece, thinkers like Thales of Miletus began to speculate about the natural world using reason rather than mythology. Thales proposed that water was the fundamental substance of the universe, thinking that all matter originated from it. Anaximander, a pupil of Thales, suggested a more abstract concept called the apeiron, an infinite and indefinite substance from which all things emerge and return. Heraclitus of Ephesus introduced the idea of change being central to the universe, encapsulated in his famous phrase, "You cannot step into the same river twice." Plato and his student Aristotle offered more complex philosophies regarding the universe's nature. Plato conceived of a cosmos fashioned by a divine craftsman, the demiurge, who imposed order on a chaotic pre-existing matter. His work, Timaeus, laid out a universe where the earth was at the center, surrounded by perfect circular motions of celestial bodies, reflecting his belief in a harmonious and ordered cosmos. Aristotle further elaborated on this geocentric model in his work, On the Heavens. He argued that the universe was finite and spherical, with Earth at its center and surrounded by concentric celestial spheres. To Aristotle, the heavens were unchanging and made up of an ethereal substance called ether, distinct from the corruptible materials found on Earth. During the Hellenistic period, philosophers like Ptolemy and Epicurus contributed significant ideas. Claudius Ptolemy's Almagest became the definitive astronomical guide for centuries, describing a comprehensive geocentric model that could predict planetary movements with reasonable accuracy. Epicurus, on the other hand, proposed an atomistic universe, influenced by Democritus, suggesting that the cosmos was composed of indivisible particles and voids, operating without divine intervention. In the Islamic Golden Age, scholars like Al-Hazen and Al-Biruni made strides in observational astronomy and experimental science, further refining the geocentric models and challenging existing paradigms. Al-Hazen's work on optics and his method of systematic experimentation influenced later scientific methods. The Renaissance and the subsequent scientific revolution ushered in transformative views of the universe, significantly departing from earlier geocentric models. Nicholas Copernicus proposed a heliocentric model, placing the sun rather than the Earth at the center of the universe. This revolutionary idea, later supported and refined by astronomers like Galileo Galilei and Johannes Kepler, laid the groundwork for Isaac Newton's laws of motion and universal gravitation, providing a mechanistic understanding of how celestial bodies interacted. These paradigm shifts not only redefined our conception of the universe, but also marked the evolution of science from philosophical speculation to empirical inquiry. Thus, early philosophers and scientists viewed the universe through a complex interplay of observation, speculation, and evolving methodologies, setting the stage for the profound advancements that came with the modern scientific era. Before the advent of modern science, the prevailing theories about the universe were largely shaped by philosophical and theological frameworks, emphasizing a harmonious and interconnected cosmos. These early models of the universe were primarily geocentric, placing Earth at the center of all cosmic activities. One of the most influential ancient theories was the geocentric model articulated by the Greek philosopher Aristotle in the 4th century BCE. Aristotle envisioned a finite spherical universe with Earth at its center. Surrounding Earth were concentric celestial spheres, each embedded with celestial objects like the moon, sun, planets, and fixed stars. These spheres were believed to move in perfect circular orbits, mirroring the perceived unchanging and eternal nature of the heavens. Aristotle also posited the existence of a fifth element, ether, which constituted the celestial realm and was distinct from the four terrestrial elements of earth, water, air, and fire. This geocentric model was further refined by Claudius Ptolemy in the 2nd century CE. Ptolemy's Almagest presented a sophisticated mathematical system that aimed to predict the positions of celestial bodies with considerable accuracy. To account for the observed retrograde motions of planets, where they appear to move backward temporarily, Ptolemy introduced complex mechanisms like epicycles and deferents. According to Ptolemy, planets moved in small circles called epicycles, while these circles themselves revolved along larger circular paths, known as deferents, centered around Earth. This intricate system, albeit not entirely accurate, provided a working model that satisfied the astronomical observations of his time. In the medieval Islamic world, scholars like al-Battani and al-Tusi further refined Ptolemaic astronomy, correcting errors and making more precise observations. Al-Tusi, for example, developed the Tusi couple, a geometric model that improved the mathematical descriptions of planetary motion within the Ptolemaic framework. Nevertheless, these scholars remained within the geocentric paradigm, as it was deeply ingrained in the philosophical and religious doctrines of their era. Concurrent with these scientific endeavors were the cosmological views inspired by religious texts. In the Judeo-Christian tradition, the universe was often depicted as a creation of a divine being. The book of Genesis describes a cosmology where God creates the heavens and the earth in a span of 6 days, with humans occupying a central and unique position in the order of creation. This theological perspective influenced medieval European scholars, who harmonized Ptolemaic astronomy with biblical teachings to form a unified, God-centered view of the cosmos. In Eastern philosophies, such as those found in ancient Indian and Chinese traditions, cosmologies were equally intricate, but differed in structure and emphasis. Hindu cosmology, for instance, envisioned a cyclic universe with periods of creation, preservation, and destruction, governed by deities like Brahma, Vishnu, and Shiva. In contrast, traditional Chinese cosmology, influenced by Taoist and Confucian thought, emphasized the harmony and balance of opposite forces, yin and yang, reflecting a universe in constant dynamic equilibrium. These prevailing theories, though varied and culturally specific, shared common themes of cosmic order, harmony, and interconnectedness. They formed the bedrock of human understanding of the universe until the paradigm shifts introduced by the scientific revolutions of the Renaissance and Enlightenment, which gradually replaced these age-old models with heliocentricity, Newtonian mechanics, and eventually the vast and dynamic universe we study today. The Big Bang Theory is the leading scientific explanation for the origin and evolution of the universe. It posits that approximately 13.8 billion years ago, the universe began as a singularity, an infinitely dense and hot point where all matter, energy, space, and time were concentrated. This singularity then underwent a massive and rapid expansion, a process not to be confused with an explosion in the conventional sense, which marked the beginning of the universe as we know it. As the universe expanded, it began to cool, allowing the formation of subatomic particles and simple elements. Within the first few minutes of this rapid expansion, known as the period of nucleosynthesis, Protons and neutrons combine to form the nuclei of hydrogen, helium, and small amounts of lithium. The universe was still incredibly hot and dense during this time, with light unable to travel freely due to constant interactions with particles. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with these nuclei, forming neutral atoms in a process called recombination. This event allowed photons to travel through space, leading to the decoupling of matter and radiation. The released photons are detectable today as the cosmic microwave background, CMB radiation, a faint but pervasive glow that fills the universe and serves as one of the strongest pieces of evidence for the Big Bang theory. Over billions of years, the gravitational attraction between particles led to the formation of stars and galaxies. These early galaxies began to cluster into larger structures under the influence of dark matter, a mysterious and invisible form of matter that interacts gravitationally but does not emit or absorb light. The continued expansion of the universe, now driven by dark energy, another enigmatic force, accelerates as time progresses. Support for the Big Bang theory comes from multiple lines of evidence. The observation that galaxies are moving away from us, with more distant galaxies receding faster, aligns with an expanding universe. This phenomenon, first noted by Edwin Hubble, is described by Hubble's law and provides a cornerstone for the Big Bang model. Additionally, the predicted abundance of light elements like hydrogen and helium aligns closely with their observed levels in the universe, supporting the theory's nucleosynthesis calculations. The Big Bang theory, through its comprehensive and testable framework, not only explains the observable data, but also provides a basis for exploring cosmic evolution. It continues to be refined and expanded by ongoing astronomical observations and theoretical advancements, allowing us to piece together the awe-inspiring chronology of the universe from its fiery beginnings to its current state and beyond. The Big Bang theory is supported by a multitude of observational evidence that collectively builds a robust case for this model of the universe's origins and evolution. These key pieces of evidence include the cosmic microwave background radiation, the expansion of the universe, the abundance of light elements, and the large-scale structure of the cosmos. One of the most compelling pieces of evidence is the cosmic microwave background, CMB radiation. Discovered by Arno Penzias and Robert Wilson in 1965, this faint glow pervades the entire universe and is considered the afterglow of the Big Bang. The CMB provides a snapshot of the universe approximately 380,000 years after the Big Bang, a time when the universe had cooled sufficiently for photons to travel freely for the first time. Measurements of the CMB, particularly those by the COBE, WMAP, and Planck satellites, reveal a nearly uniform temperature with slight variations. These tiny fluctuations correspond to the seeds of all current cosmic structure, indicating the initial conditions that led to the formation of galaxies and larger cosmic structures. The observable expansion of the universe is another cornerstone of the Big Bang theory. In the 1920s, Edwin Hubble observed that galaxies are moving away from us, with more distant galaxies receding at faster rates. This phenomenon, known as Hubble's law, is consistent with an expanding universe and suggests that all galaxies were once closer together in the distant past. The relationship between the distance of galaxies and their redshift, a shift toward the red end of the spectrum due to their motion away from us, provides direct evidence for this expansion, which aligns with the predictions of the Big Bang model. The relative abundance of light elements, specifically hydrogen, helium, and trace amounts of lithium, also supports the Big Bang theory. During the first few minutes after the Big Bang, conditions were hot and dense enough for nuclear fusion to occur, forming these light elements in a process known as Big Bang nucleosynthesis. The predicted ratios of these elements, about 75% hydrogen and 25% helium by mass, match remarkably well with their observed abundances in the oldest known stars and gas clouds, further validating the theory. Additionally, the large-scale structure of the universe, revealed through observations of galaxy clusters and the cosmic web, supports the Big Bang theory. Galaxies are not randomly distributed, but instead form a complex network of filaments and voids, patterns that match the fluctuations seen in the CMB. These structures likely arose from the gravitational collapse of initial density fluctuations present in the early universe, as predicted by the Big Bang model. Together, these lines of evidence create a consistent and compelling picture of a universe that has been expanding and evolving over the past 13.8 billion years. While the Big Bang theory continues to be refined and explored through new observations and theoretical advancements, the core evidence firmly establishes it as the leading explanation for the origin and development of our cosmos. The acceptance of the Big Bang theory by the scientific community was a gradual process that evolved through a combination of theoretical insights, observational evidence, and advancements in technology over the course of the 20th century. This journey was marked by several key milestones and contributions from numerous scientists. The story begins in the early 20th century with Albert Einstein's theory of general relativity, which fundamentally changed our understanding of gravity and the dynamics of space and time. In 1917, Einstein applied his equations to the universe as a whole, but added a cosmological constant to maintain a static universe, as it was the prevailing belief at the time. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that galaxies are moving away from us, indicating that the universe is expanding. This observation was pivotal because it suggested that the universe had a beginning, contradicting the notion of a static, eternal universe. Simultaneously, Russian physicist Alexander Friedmann and Belgian priest and astronomer Georges Lemaitre independently proposed models of an expanding universe, deriving solutions to Einstein's equations that did not require a static cosmos. Lemaitre, in particular, introduced the idea of a primeval atom, an initial highly concentrated state from which the universe expanded. Despite these advancements, the idea of a dynamic universe was still met with skepticism until further observational evidence came to light. In the mid-20th century, British astrophysicist Fred Hoyle and his colleagues proposed the steady-state theory as an alternative. This theory posited a continuous creation of matter to explain the universe's expansion while maintaining a constant average density. The tide began to turn in favor of the Big Bang theory with a series of crucial discoveries. In 1948, Ralph Alpha and George Gamow predicted that the early universe would have been hot and dense enough to create light elements through nucleosynthesis. This prediction led to the calculation of the relative abundances of hydrogen and helium, which matched observations and provided support for the Big Bang model. The most significant observational breakthrough came in 1965 when Arno Penzias and Robert Wilson discovered the cosmic microwave background, CMB radiation. This faint signal, a remnant of the early universe, was the afterglow of the Big Bang and matched predictions perfectly. The CMB provided concrete evidence of a hot, dense origin of the universe, leading to a rapid shift in scientific consensus. Further bolstering the Big Bang theory were observations made by satellite missions like COBE, WMAP, and the Planck satellite, which mapped the CMB with increasing precision. These observations revealed the tiny fluctuations in temperature that corresponded to the seeds of large-scale cosmic structures. Additionally, the detection of the universe's accelerating expansion in the late 1990s, attributed to dark energy, provided further support for the Big Bang framework. As these pieces of evidence accumulated, the Big Bang theory became the leading cosmological model, unifying observations of the universe's large-scale structure, the abundance of light elements, and the CMB. This convergence of theoretical predictions and empirical data led to the broad acceptance of the Big Bang theory in the scientific community, shaping our modern understanding of the universe's origin and evolution. The story of the universe begins with the Big Bang, a term that refers not to an explosion but to an expansion, a rapid and profound unfolding of energy and matter. It all started approximately 13.8 billion years ago when our universe was condensed into an incredibly hot and dense singularity, far smaller than the tip of a pin. The first stage of the Big Bang is called the Planck epoch, lasting until just 10 to the negative 43rd seconds after the inception of the universe. During this infinitesimally short period, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. Conditions were so extreme that conventional physics as we know it fails to describe them, necessitating a blend of quantum mechanics and general relativity, which remains elusive to scientists even today. As the universe continued to expand and cool, it transitioned into the inflationary epoch, a blink of an eye in cosmic terms, occurring around 10 to the negative 32nd seconds after the Big Bang. During this phase, the universe underwent exponential growth, stretching space itself faster than the speed of light, a phenomenon allowed because it's not matter, but the fabric of space expanding. Then we reach the quark epoch, which took place roughly between 10 to the negative 12th seconds to 10 to the negative 6th seconds. During this period, conditions cooled enough for quarks, the fundamental constituents of protons and neutrons, to form. As the universe cooled further, quarks began to combine, leading to the formation of protons and neutrons during the Hadron epoch. Subsequently, within the first 3 minutes post-Big Bang, these particles fused to form the first light nuclei, marking the nucleosynthesis era. From these humble beginnings emerged the building blocks of matter, leading eventually to atoms, stars, galaxies, and the universe as we observe it today. In the first fleeting moments after the Big Bang, the universe underwent a series of rapid and transformative changes that set the stage for everything to come. Initially, in less than a trillionth of a second, the universe was in a state of unimaginable density and temperature, a seething broth of fundamental particles. As the universe expanded, it began to cool, allowing forces and particles to differentiate and become distinct. Within the first second, a pivotal era known as the quark epoch unfolded. During this phase, the universe was still incredibly hot, but cooling rapidly. Quarks, which are the building blocks of protons and neutrons, roamed freely in a dense plasma. As the temperature continued to drop, quarks began to form into protons and neutrons, which are the core components of atomic nuclei. This process wrapped up within the first few microseconds. Around this same period, leptons, including electrons, started to decouple from the primordial soup, setting the stage for atoms to form later on. In addition to the formation of these particles, the universe became transparent to neutrinos, a class of extremely light and weakly interacting particles, during the lepton epoch, seconds after the Big Bang. This transparency allowed neutrinos to spread throughout the cosmos, a process still detectable today in what we call the cosmic neutrino background. As this first second approached its end, electromagnetic interactions began to manifest more prominently, and photons started to play a significant role. However, it would still be thousands of years before the universe cooled sufficiently for matter and radiation to decouple fully, leading to the formation of the first stable atoms, and much later, the stars and galaxies that illuminate our night sky. The cosmic microwave background radiation, often abbreviated as CMB, serves as a time capsule from the adolescent universe, providing us with a snapshot of the cosmos roughly 380,000 years after the Big Bang. This radiation is the residual thermal energy from that era, now cooled to just under 3 degrees Kelvin, or a touch above absolute zero. At its inception, the universe was dense and hot enough that atoms couldn't form. Protons and electrons floated freely in a hot, opaque plasma. As the universe expanded and cooled, these charged particles combined to form neutral hydrogen atoms in an event known as recombination. When this recombination occurred, photons, particles of light, were no longer scattered by free electrons and could finally travel freely through space. This event marked the universe's transition from an opaque fog to a transparent expanse, allowing light to stream across the cosmos uninterrupted. The CMB is essentially this first light, stretched into microwave wavelengths by billions of years of cosmic expansion. The significance of the cosmic microwave background lies in the wealth of information it carries about the early universe. Tiny fluctuations in temperature and density within the CMB map reveal the seeds of all future structure, the galaxies, clusters, and superclusters we observe today. These variations have been scrutinized by satellites like COBE, WMAP, and Planck, revealing not only the age and composition of the universe, but also bolstering the Big Bang theory itself. By studying the CMB, cosmologists can test predictions about the universe's infancy, offering crucial insights into its origins, its large-scale structure, and the fundamental physical laws that govern its evolution. Observing the afterglow of the Big Bang, known as the cosmic microwave background radiation, CMB, is akin to peering back through the eons to catch a glimpse of the universe in its infancy. This faint glow permeates the cosmos, detectable in every direction and remarkably uniform, with only minute fluctuations that hold a trove of cosmological information. To detect and study this ancient light, scientists employ specialized instruments, both ground-based and space-based, which are finely tuned to the microwave part of the electromagnetic spectrum. Space missions have been particularly crucial in this endeavor, with satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite leading the charge. COBE was the trailblazer, launched in 1989, providing the first precise measurements of the CMB's temperature and spectrum, confirming it as the relic radiation from the Big Bang. WMAP, launched in 2001, delivered a more detailed map of temperature fluctuations, fine-tuning our understanding of the universe's age, composition, and development. The most precise observations to date come from the Planck satellite, which was launched in 2009. Planck's highly sensitive instruments measured the CMB's temperature variations with unprecedented resolution, allowing cosmologists to test theories about the universe's initial conditions and the nature of dark matter and dark energy. Ground-based observatories, such as those located at high altitudes or in Antarctica, supplement these space missions. Places like the Atacama Desert in Chile and the South Pole provide pristine conditions, free from atmospheric interference, to study the CMB. Projects like the Atacama Cosmology Telescope, ACT, and the South Pole Telescope, SPT, continue to provide valuable data, contributing to the 3D map of the universe's structure and its evolution over time. Through these sophisticated efforts, the afterglow of the Big Bang becomes not just a relic of the past, but a powerful tool, illuminating the mysteries of our cosmic origins and the fundamental forces that have shaped the universe as we know it. Quantum fluctuations are one of the most captivating and profound aspects of quantum mechanics, representing tiny temporary changes in the amount of energy in a point in space. They arise from the Heisenberg uncertainty principle, which states that it is impossible to simultaneously know both the precise position and momentum of a particle. This fundamental principle implies that the vacuum of space is not actually empty, but teems with temporary pairs of particles and antiparticles that pop in and out of existence, fleetingly borrowing energy from their surroundings before annihilating each other and returning that energy. These ephemeral fluctuations have significant implications for the fabric of the cosmos. In the early universe, during the incredibly brief yet consequential period of cosmic inflation, these minuscule quantum jitters were amplified to macroscopic scales. As space itself expanded exponentially, quantum fluctuations stretched out, seeding tiny variations in density that would later grow into the vast cosmic structures we observe today. It's these initially microscopic differences that eventually led to the large-scale distribution of matter in the universe, forming galaxies, clusters, and voids. The fingerprints of quantum fluctuations are imprinted on the cosmic microwave background radiation. Those slight temperature fluctuations we observe in the CMB are essentially the magnified echoes of quantum jitters from the dawn of time. In this way, quantum mechanics not only dictates the behavior of particles at the smallest scales, but also shapes the very large-scale structure of the universe. By studying these fluctuations, scientists continue to unravel the complex interplay between quantum forces and cosmic evolution, gaining deeper insights into the fundamental workings of reality itself. Quantum fluctuations, those tiny ephemeral jitterings in the fabric of space-time, have the remarkable ability to catalyze the creation of particles through a variety of fascinating mechanisms. At their core, quantum fluctuations arise from the Heisenberg uncertainty principle, a fundamental concept of quantum mechanics which states that certain pairs of physical properties, such as position and momentum, cannot both be precisely measured simultaneously. This principle implies that what we consider vacuum is not a void, but rather a frothing expanse of potential, teeming with transient bursts of energy. One significant process by which quantum fluctuations can lead to particle creation is known as pair production. In pair production, energy borrowed from the quantum vacuum materializes as a particle-antiparticle pair. These pairs usually annihilate each other almost instantaneously, returning the borrowed energy. However, in the presence of a strong electromagnetic field, such as around a black hole's event horizon or within powerful particle accelerators, these pairs can be separated before they annihilate. If the particle-antiparticle pair gains enough energy from their surroundings, they can become real, lasting particles contributing to the observable matter in the universe. Moreover, during the rapid expansion of the early universe, known as cosmic inflation, quantum fluctuations were stretched to macroscopic scales. This stretching caused tiny perturbations in the density of the energy field permeating the universe. As inflation ended and the universe began to cool, these perturbations led to regions of slightly higher or lower energy density. In areas with higher energy density, conditions became ripe for converting that energy into particles. This process, known as reheating, essentially meant that the energy contained in those quantum fluctuations was transformed into a hot, dense brew of particles, a genesis event that seeded the universe with the matter and radiation we observe today. Thus, through these mechanisms, quantum fluctuations do far more than just fleetingly borrow energy. They lay the foundation for particle creation, contributing to the birth and evolution of the cosmos itself, echoing the profound interconnectedness of the quantum realm and the grand tapestry of the universe. Vacuum energy is a concept that seems almost paradoxical at first glance. It is the energy that is present even in the most seemingly empty stretches of space, devoid of matter or radiation. In classical physics, a vacuum would be characterized as an absolute void, a true nothingness. However, quantum mechanics reveals that even this void teems with activity due to the incessant dance of virtual particles. This ceaselessly fluctuating sea of virtual particles and fields contributes to a baseline level of energy, known as vacuum energy. The existence of vacuum energy is fundamentally tied to the Heisenberg uncertainty principle, which implies that energy levels within any given point in space are never truly zero. This has profound implications for our understanding of the universe. One of the more compelling manifestations of vacuum energy is the Casimir effect. When two uncharged parallel metal plates are placed extremely close to each other in a vacuum, they experience an attractive force not attributable to any conventional electromagnetic force, but rather to the reduction in virtual particles between the plates compared to those outside. This effect offers a tangible glimpse into the subtle influence of vacuum energy. Vacuum energy is also a key player in contemporary cosmology, particularly in relation to the mysterious phenomenon known as dark energy. Observations of distant supernovae and the cosmic microwave background radiation suggest that the universe's expansion is accelerating, a phenomenon that could be driven by a form of vacuum energy. This dark energy, which constitutes about 70% of the total energy in the universe, is thought to be some manifestation of vacuum energy that generates a repulsive force counteracting gravitational attraction, driving galaxies apart at an accelerating rate. In summary, vacuum energy is the undercurrent of the quantum world, a baseline hum of activity that persists throughout the universe. It challenges our classical notions of emptiness and reveals an intricate layer of the cosmos at both quantum and cosmological scales. Whether in the manifestation of the Casimir effect or the universe's accelerating expansion, vacuum energy serves as a testament to the profound and often counterintuitive nature of reality as dictated by quantum mechanics. The concept of vacuum energy is intrinsically linked to our understanding of the universe's origin and its subsequent evolution. In the earliest moments following the Big Bang, especially during the period known as cosmic inflation, vacuum energy played a pivotal role in shaping the cosmos as we observe it today. Immediately after the Big Bang, the universe was in an extremely hot, dense state where the laws of classical physics break down, necessitating a quantum mechanical description. During this time, a scalar field often called the inflaton field dominated the dynamics of the universe. The energy associated with this field can be considered a form of vacuum energy because it was not tied to any particles or radiation, but rather to the underlying fabric of space-time itself. This inflaton field generated a repulsive force that drove an exponential expansion of space known as cosmic inflation, which smoothed out any irregularities and homogenized the observable universe. As the universe expanded, quantum fluctuations in this vacuum energy field were stretched to macroscopic scales, seeding tiny density variations. These fluctuations are the genesis points that, over billions of years, evolved into the large-scale structure of the universe, including galaxies, clusters, and the cosmic web. This mechanism illustrates how quantum phenomena at the tiniest scales have profound implications for the structure and evolution of the cosmos. Furthermore, as cosmic inflation drew to a close, the vacuum energy of the inflaton field decayed, converting its energy into a hot, dense plasma of particles in an event known as reheating. This phase transition marks the transition from the inflationary period to the hot Big Bang, effectively setting the stage for the universe we inhabit today. The energy released during this process fueled the subsequent formation of matter and radiation, laying down the blueprint for the universe's ongoing expansion. In summary, vacuum energy is not just an abstract concept, but a fundamental player in the grand cosmic narrative. It induced the rapid early expansion of space, imprinted the initial conditions for cosmic structure, and facilitated the transition from a quantum-dominated early universe to the classical universe filled with matter and radiation. Through these roles, vacuum energy underscores the profound connections between the quantum realm and the vast expanse of the cosmos, each influencing the other in ways that continue to intrigue and challenge our understanding. The idea that something can come from nothing due to the principles of quantum mechanics is one of the most intriguing and counterintuitive concepts in modern physics. At the heart of this notion is the quantum vacuum, which, far from being an empty void, is a seething expanse filled with fluctuating energy and virtual particles that pop in and out of existence. This restless activity stems from the Heisenberg uncertainty principle, which dictates that the exact energy of any given point in space cannot be pinned down precisely. Instead, there is always some inherent uncertainty. In the quantum vacuum, these fluctuations momentarily spawn pairs of particles and antiparticles. These virtual particles generally annihilate each other almost instantly, but for the brief period they exist, they embody the concept that something can indeed come from nothing. This phenomenon is experimentally supported by the Casimir effect, where the presence of closely positioned metal plates in a vacuum affects the density of virtual particles between them, resulting in a measurable force. On a grander cosmic scale, these quantum fluctuations may have played a crucial role in the creation of the universe itself. The theory of cosmic inflation suggests that a period of rapid expansion stretched these minute fluctuations to macroscopic scales, ultimately seeding the large-scale structures we observe today. Moreover, modern cosmology posits that the universe could have emerged from a primordial quantum state, driven by fluctuations in an underlying quantum field. This aligns with the concept of vacuum energy, where energy is intrinsic to the fabric of space, even in the absence of matter and radiation. Stephen Hawking and other leading physicists have suggested that universes might spontaneously emerge from the quantum vacuum due to these fluctuations, much like virtual particles. This notion leads to the hypothesis of a multiverse, with countless universes continually coming into and out of existence, each governed by its own set of physical laws. While this idea remains speculative and beyond direct observational verification, it offers a framework to understand how the Big Bang of our own universe could originate from a quantum fluctuation. Therefore, within the framework of quantum mechanics, the notion that something can come from nothing is not just a philosophical musing, but a scientifically grounded possibility. It challenges our classical intuitions and opens up profound questions about the nature of existence and the origins of our universe, suggesting that the boundary between something and nothing is far more permeable than we might have imagined. Virtual particles are a fascinating and somewhat elusive concept in quantum mechanics. They are not particles in the traditional sense, but are transient fluctuations that appear and disappear within the quantum vacuum. Existing only for brief moments, they defy the classical view of particles as permanent, tangible entities. Instead, virtual particles are a manifestation of the Heisenberg uncertainty principle, which permits energy and particle existence to be uncertain over very short timescales. The role of virtual particles is profound and diverse, contributing significantly to the interactions that govern fundamental physical processes. One of their primary roles is in mediating forces between actual particles. For instance, in quantum electrodynamics, QED, the force between charged particles, such as electrons and protons, is mediated by the exchange of virtual photons. Though these photons are never directly observed, their exchange results in the electromagnetic force. Similarly, virtual particles like W and Z bosons mediate the weak nuclear force responsible for radioactive decay processes. Gluons, the carriers of the strong nuclear force, are also virtual particles that bind quarks together within protons and neutrons. Virtual particles also have observable consequences through phenomena like the Casimir effect. When two uncharged parallel metal plates are placed very close together, the difference in vacuum energy due to virtual particles between the plates versus outside them generates an attractive force. This force is experimentally measurable and provides a tangible effect of virtual particles' existence. Another compelling role of virtual particles appears near black holes, specifically in the context of Hawking radiation. According to Stephen Hawking, near the event horizon of a black hole, pairs of virtual particles can be split apart by gravitational forces. One particle falls into the black hole, while the other escapes into space as real radiation. This process leads to the gradual loss of mass and energy from the black hole, ultimately resulting in its evaporation over astronomical timescales. Furthermore, virtual particles are pivotal in the quantum field theory description of vacuum polarization. In this process, the presence of a charged particle in the vacuum causes virtual electron-positron pairs to momentarily appear and modulate the charge distribution around the particle, effectively altering the observed charge and the electromagnetic interactions. In summary, virtual particles are transient and typically undetectable in isolation, yet they are indispensable to the mechanisms underlying fundamental forces and quantum phenomena. From mediating interactions between real particles to enabling black hole radiation, virtual particles serve as the hidden scaffolding of the quantum world, allowing the universe to function in ways that classical physics could never predict. They represent a key element bridging the gap between the abstract mathematical formulations of quantum mechanics and the tangible physical effects we can observe and measure. The quest to understand the origin of the universe has led to the development of several cosmological models, each offering unique perspectives on how the cosmos began and evolved. These models blend observations with theoretical frameworks, ranging from classical theories to more speculative propositions grounded in advanced physics. The most prevalent and widely accepted model is the Big Bang theory, which posits that the universe began approximately 13.8 billion years ago from an extremely hot and dense singularity. According to this model, the universe has been expanding ever since, leading to the relatively cool, vast cosmos we observe today. The theory is strongly supported by observational evidence, such as the cosmic microwave background, CMB radiation, the abundance of light elements like hydrogen and helium, and the redshift of distant galaxies, which indicates that the universe is expanding. Enhancing the Big Bang theory is the concept of cosmic inflation. Proposed by physicist Alan Guth in the early 1980s, the inflationary model suggests that a rapid exponential expansion of space occurred within the first fraction of a second after the Big Bang. This brief period of inflation smoothed out any initial irregularities, providing an explanation for the large-scale uniformity of the universe and the tiny fluctuations in the CMB that eventually led to galaxies and larger cosmic structures. Another intriguing hypothesis is the cyclic model, which posits that the universe undergoes endless cycles of expansion and contraction. In this scenario, the Big Bang is not an isolated event, but part of a recurring cycle driven by the physics of cosmic brains and string theory. Prominent variants of this model include the ekpyrotic universe, where collisions between brains in higher dimensional space trigger repeated cycles of cosmic birth and death. While more speculative than the Big Bang model, cyclic models aim to address puzzles such as the universe's initial conditions and the nature of dark energy. The steady-state theory, once a popular alternative to the Big Bang, proposes that the universe has no beginning or end but remains in a constant state, with new matter continuously created to maintain a constant density as it expands. Although this model accounted for the observed expansion, it fell out of favor primarily due to its inability to explain the CMB and the accumulation of observational evidence supporting the Big Bang. Quantum mechanics also contributes to cosmological modeling with ideas like the quantum creation of the universe. This model suggests that the universe could have spontaneously originated from a quantum vacuum fluctuation driven by the principles of quantum mechanics. Stephen Hawking and James Hartle proposed a no-boundary condition, where time behaves like another dimension of space at the universe's inception, smoothing out the singularity and enabling a quantum birth from nothing. Finally, there are more exotic theories such as the multiverse hypothesis, which proposes that our universe is just one of potentially infinite parallel universes within a larger multiverse. Each universe could have different physical constants and laws. This hypothesis often arises from interpretations of inflationary theory and string theory, suggesting that different regions of space could inflate at varying rates, leading to distinct, causally disconnected universes. In summary, while the Big Bang theory, bolstered by cosmic inflation, remains the dominant model explaining the origin and development of the universe, other models like the cyclic universe, steady state, quantum creation, and multiverse hypothesis offer compelling alternatives or extensions. These cosmological models reflect humanity's ongoing endeavor to decode the mysteries of the cosmos, each contributing unique insights and posing new questions about the nature of existence and the ultimate origins of our universe. The steady-state theory and the Big Bang theory offer fundamentally different perspectives on the origin, structure, and evolution of the universe. These two models diverge in their assumptions about whether the universe had a beginning and how it has changed over time. The Big Bang theory posits that the universe began approximately 13.8 billion years ago from an extremely hot and dense state, often referred to as a singularity. According to this theory, the universe has been expanding ever since, cooling and evolving to form the galaxies, stars, and planets we observe today. Key pieces of supporting evidence for the Big Bang theory include the cosmic microwave background, CMB radiation, which is the afterglow of the early universe, and the observed redshift of distant galaxies, indicating that the universe is still expanding. Additionally, the Big Bang model accurately predicts the relative abundances of light elements, such as hydrogen and helium produced during the first few minutes after the initial explosion, a process known as Big Bang nucleosynthesis. In contrast, the steady-state theory posits a universe that has neither a beginning nor an end, maintaining a constant average density over time despite its continual expansion. Proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi in 1948, this theory suggests that new matter is continuously created to fill the void left by the expanding universe, allowing it to remain in a steady state. In this model, the universe is eternal and unchanging on large scales, meaning it always looks the same at any point in time and space. This continuous creation of matter happens at such a slow rate, about 1 hydrogen atom per cubic meter per billion years, that it evades direct detection. One of the primary differences between the two theories is their predictions about the background radiation of the universe. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory and posed a significant challenge for the steady-state theory. The uniform and isotropic nature of the CMB fits well with the Big Bang model, which predicts that this radiation is the relic heat left over from the early universe when it was much hotter and denser. Moreover, observations of distant galaxies and quasars support the notion of an evolving universe. The Big Bang theory accommodates these observations by suggesting that the universe looked different in the past, showing younger galaxies and a more active state of star formation. In contrast, the steady-state theory would require the properties of galaxies and other cosmic structures to remain constant over time, which is inconsistent with the accumulating observational data showing an evolving universe. While the steady-state theory presents an elegant and unchanging view of the cosmos with continuous matter creation, it struggles to account for key observations, such as the cosmic microwave background radiation and the evolving nature of galaxies. The Big Bang theory, with its framework of a universe that began from a hot, dense state and has been expanding and cooling ever since, offers a more comprehensive and supported explanation for the multitude of phenomena we observe in the cosmos. The cyclic model of the universe is a fascinating and speculative alternative to the conventional Big Bang theory. Unlike the standard model, which posits a singular beginning with a subsequent expansion, the cyclic model envisions the cosmos undergoing endless cycles of birth, evolution, and rebirth. These cycles could each last over vast timescales, hundreds of billions or even trillions of years, resulting in a universe that periodically renews itself. One of the most well-known cyclic models is the ekpyrotic universe, which draws from ideas in string theory and higher-dimensional cosmology. In this model, our visible universe is a three-dimensional membrane, or brane, situated in a higher-dimensional space. This brane periodically collides with a parallel brane, releasing enormous amounts of energy that effectively initiate a new cycle of expansion and contraction. Each collision produces a Big Bang-like event, setting the stage for the creation of matter and radiation, similar to the start of a new cycle. The term ekpyrotic is derived from the Greek word for conflagration, symbolizing a fiery rebirth from destruction. The cyclic model offers potential explanations for several perplexing cosmological issues. For instance, during each contraction phase, any irregularities and anisotropies in the universe's structure could be smoothed out by a mechanism similar to inflation in the traditional Big Bang model. This would ensure a homogeneous and isotropic starting point for each new cycle. Moreover, the cyclic framework could potentially provide an elegant explanation for the smallness of the cosmological constant, a parameter that describes the energy density of the vacuum and drives the universe's current accelerated expansion. In the cyclic context, this constant might be dynamically adjusted over each cycle, alleviating the fine-tuning problems that plague other models. However, the cyclic model also introduces new challenges and unanswered questions. A critical concern is how each cycle transitions from contraction to expansion without resulting in a singularity, a point of infinite density where conventional physics breaks down. Theoretical physicists work on resolving these issues by employing advanced mathematical frameworks and extending ideas from quantum gravity and string theory. Additionally, observational evidence presents hurdles. The cosmic microwave background, CMB, radiation's highly uniform nature, and the large-scale structure of the universe have traditionally been interpreted within the context of a single expanding universe. While the cyclic model needs to replicate these observations' successes, it must also make unique predictions that can be tested through astrophysical measurements. In summary, the cyclic model posits a universe in a state of perpetual renewal, cycling through phases of birth, expansion, contraction, and rebirth. This perspective provides innovative solutions to cosmological puzzles like the horizon problem and the cosmological constant, but it also introduces complex challenges that remain subjects of active research. Embracing this model requires reconciling it with existing observations while continuing the quest for a deeper understanding of the universe's fundamental workings. As theoretical physics advances and observational techniques improve, the cyclic model may either find its evidence or yield to more comprehensive theories regarding the cosmos's nature. The multiverse theory posits that our universe is just one of potentially infinite universes that exist in a vast and possibly infinite multiverse. These parallel universes, collectively known as the multiverse, may be entirely separate from one another, each with its own distinct physical laws, constants, and conditions. The multiverse concept arises from several lines of theoretical inquiry, including cosmic inflation, string theory, and quantum mechanics, each offering a different but complementary perspective on how multiple universes could exist. One of the most prominent versions of the multiverse theory comes from the idea of eternal inflation. Developed from the inflationary model of the Big Bang, eternal inflation suggests that cosmic inflation didn't just stop uniformly, but instead continues in isolated pockets within a much larger inflating space. These pockets, or bubble universes, stop inflating and form distinct separate universes, one of which is our own. In this scenario, each bubble universe could have different physical properties, resulting from the quantum fluctuations that dictated their formation. This process leads to a diverse multiverse, where our universe is just one outcome among countless possibilities. String theory provides another fertile ground for the multiverse concept. Within string theory's framework, the space of possible configurations, often referred to as the landscape, is vast. Each configuration corresponds to a potential universe with its own set of physical laws and constants. These configurations arise from the different ways extra dimensions can be compactified. adding layers of complexity to the potential structure of the multiverse. On a more speculative level, the many worlds interpretation of quantum mechanics also suggests a form of the multiverse. In this interpretation, every quantum event that could potentially happen does happen, but in separate, non-communicating branches of the universe. This means that with every decision or random event, the universe splits into parallel versions, each representing one possible outcome. While conceptually different from the cosmic inflation or string theory multiverses, it adds to the idea that our universe is not alone, but part of a vast ensemble of realities. The multiverse theory has profound implications for our understanding of the universe's origin. One significant consequence is the potential explanation for the fine-tuning observed in our universe. Many physical constants appear to be precisely set to allow for the existence of stars, galaxies, and life. In a multiverse with an enormous variety of universes, it's conceivable that only a small fraction have the right conditions for life as we know it. Our universe, then, could be one of the few where the physical constants happen to fall into the narrow range that permits complex structures and biological life, a situation often referred to as the anthropic principle. While the multiverse theory offers tantalizing possibilities, it's important to note that it currently remains largely speculative and beyond direct empirical verification. Observational evidence for other universes is challenging to obtain since they would likely be causally disconnected from ours, making interactions impossible with our current understanding of physics. However, some theoretical predictions within the multiverse framework could indirectly influence observable phenomena in our universe, such as imprints on the cosmic microwave background from bubble collisions or specific signatures in particle physics experiments. In conclusion, the multiverse theory suggests that our universe is one of many, each with unique properties and origins. It provides a potential framework for understanding the origin and fine-tuning of our universe, but also poses significant challenges in terms of empirical validation. As our theoretical models and observational technologies advance, the multiverse theory continues to be a compelling topic of research poised at the frontier of modern cosmology and theoretical physics. Inflation theory is a cornerstone of modern cosmology, offering a profound explanation for the universe's rapid expansion during its earliest moments. Proposed by physicist Alan Guth in the early 1980s, the theory posits that a brief period of exponential expansion occurred a mere fraction of a second after the Big Bang. This phase of inflation lasted an incredibly short time, around 10 to the negative 36th to 10 to the negative 32nd seconds, but had a dramatic impact on the universe's structure and evolution. Inflation theory addresses several key issues that arose from the traditional Big Bang model. One of the most pressing problems is the horizon problem. According to the Big Bang theory, regions of the universe separated by vast distances should not have had enough time to come into thermal equilibrium due to the finite speed of light and the relatively young age of the universe. However, the uniformity of the cosmic microwave background radiation, CMB, across the sky suggests that these regions did somehow reach the same temperature. Inflation resolves this by proposing that all parts of the observable universe were once causally connected in a much smaller, more uniform space before being stretched apart by rapid expansion. Another issue is the flatness problem. Observations indicate that the universe is remarkably close to being geometrically flat, meaning its overall density is very close to the critical value that separates a universe that will eventually collapse from one that will expand forever. For the universe to be as flat as it appears today, the initial conditions would need an extremely fine-tuned balance. The rapid expansion during inflation would dilute any initial curvature, driving the universe toward flatness, much like the way a small piece of a curved surface appears flat when viewed up close. Inflation also provides a mechanism for the generation of primordial density fluctuations. Quantum fluctuations in the inflaton field, the hypothetical scalar field that drove inflation, were stretched to macroscopic scales during the rapid expansion. These quantum fluctuations became classical perturbations in the density of matter and energy. Over time, these tiny perturbations grew under the influence of gravity, eventually leading to the formation of galaxies, clusters, and the large-scale structure of the universe we observe today. This prediction aligns with the observed slight temperature variations in the CMB, which serve as snapshots of these early density fluctuations. The theory of inflation has received substantial observational support. The detailed measurements of the CMB, particularly by satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have provided data that match the predictions of inflationary models. These observations include the uniformity and slight anisotropies in the CMB, which correspond to the density fluctuations seeded during inflation. Inflation theory also seamlessly integrates with particle physics. The precise nature of the inflaton field is still a topic of research, with various candidates proposed, including fields from supersymmetry and grand unified theories. These connections bridge the gap between cosmology and high-energy physics, offering a more unified picture of fundamental forces and the universe's youngest moments. In summary, inflation theory profoundly transforms our understanding of the universe's early expansion, addressing critical issues like the horizon problem, flatness problem, and the origin of large-scale structure. With robust theoretical foundations and strong observational support, it remains a pivotal and compelling framework in cosmological studies, continually guiding our quest to comprehend the universe's origins and evolution. In the grand tapestry of our universe, dark matter and dark energy weave threads that remain largely mysterious, yet are crucial to the fabric's integrity. Scientists estimate that only about 5% of the universe is composed of the familiar visible matter that forms stars, planets, and galaxies. The remaining 95% is split between dark matter and dark energy, with dark matter constituting roughly 27% and dark energy a staggering 68%. Dark matter, though invisible and elusive, behaves like cosmic scaffolding, holding galaxies together with its gravitational pull. Without it, galaxies would not have the structural integrity to withstand their own rotational speeds. Yet, despite its critical role, dark matter does not interact with electromagnetic forces. It neither emits nor absorbs light, making it detectable only through its gravitational effects. On the other hand, dark energy is even more enigmatic. It's the unseen force driving the universe's accelerated expansion, a discovery that upended prior cosmological models. While dark matter binds the universe, dark energy pushes it apart, both forces integral to the complex dance of cosmic evolution. The universe's beginning, often referred to as the Big Bang, presents a mind-boggling scenario where the laws of physics as we know them were both incredibly relevant and uniquely challenged. Approximately 13.8 billion years ago, the universe was compressed into a singularity, a point of infinite density and temperature. During this infinitesimally brief moment, known as the Planck epoch, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. However, the conditions were so extreme that our current understanding of physics, including general relativity and quantum mechanics, becomes incomplete and potentially divergent. As the universe began to expand and cool, it transitioned through various epochs where the laws of physics gradually took their forms. Within the first fraction of a second, the fundamental forces differentiated from one another. The quark-gluon plasma, a state of matter where quarks and gluons roamed freely, eventually condensed to form protons and neutrons. As the universe continued to cool over the course of thousands of years, atoms began to form, leading to the creation of the first simple elements like hydrogen and helium. It was during these early moments that the universe's fundamental properties were set, governed by the same physics laws that dictate the motion of galaxies, the life cycle of stars, and even the behavior of particles in a laboratory today. These astonishing transitions illustrate how the laws of physics not only apply, but actually emerged and evolved from the universe's nascent chaos. General relativity, formulated by Albert Einstein in 1915, fundamentally reshaped our comprehension of gravity and the fabric of space-time, offering profound insights into the universe's origin. Unlike the earlier Newtonian conception of gravity as a mere force between masses, general relativity describes gravity as the curvature of space-time caused by mass and energy. This paradigm shift enables us to understand the dynamics of cosmic structures on a grand scale, revealing how massive objects like stars, planets, and even light navigate the contours of this curved space-time. In the context of the universe's origin, general relativity provides the mathematical framework for the Big Bang theory. According to Einstein's equations, the cosmodynamic history of the universe can be traced back to a singular, incredibly dense and hot point, a singularity. This singularity marks the starting point of space-time itself, around 13.8 billion years ago. Solutions to these equations, such as the famous Friedmann-Lemaitre-Robertson-Walker metric, describe how the universe expands over time. Importantly, general relativity also predicts phenomena such as the cosmic microwave background radiation, a remnant heat from the Big Bang, which has been observed and measured, offering compelling evidence for this model. Thus, general relativity not only aids in conceptualizing the universe's beginnings, but continues to be an indispensable tool in exploring the vast cosmic expanse and its evolution. Quantum mechanics and cosmology may seem like they belong to vastly different realms, one dealing with the minuscule particles and the other with the vastness of the universe. However, these two fields intersect intriguingly at the very boundaries of our understanding of the cosmos. Quantum mechanics governs the behavior of particles at the smallest scales, where the bizarre principles of superposition, entanglement, and uncertainty rule. On the other hand, cosmology studies the universe's birth, evolution, and large-scale structure. This intersection is especially pronounced when considering the universe's earliest moments, or the Planck epoch, a period so minuscule in time that quantum effects dominated the macroscopic scale. In the moments following the Big Bang, the universe was so compact and hot that quantum fluctuations, tiny momentary changes in energy levels, played significant roles. These fluctuations are believed to have been amplified during cosmic inflation, a rapid exponential expansion of the universe in its earliest phase, seeding the large-scale structures we observe today, such as galaxies and galaxy clusters. Moreover, theories that aim to unify general relativity with quantum mechanics, such as string theory or quantum gravity, strive to explain these early moments comprehensively. Concepts like the multiverse arise from these endeavors, suggesting that our universe might be just one of many, each with different physical laws and constants. By probing these foundational intersections, scientists hope to uncover a theory of everything that can seamlessly integrate the quantum and cosmic scales, offering a more profound understanding of the cosmos from its tiniest particles to its grandest phenomena. This quest remains one of the most exciting and challenging endeavors in modern physics. Singularities are regions in spacetime where the gravitational field becomes infinitely strong, leading to a breakdown in the known laws of physics. These points are characterized by tremendous densities and infinitesimal volumes, causing the mathematical descriptions of spacetime to reach undefined values. Singularities are most famously associated with black holes, regions of space where the gravitational pull is so intense that not even light can escape. In these cosmic anomalies, the core collapses into a point-like singularity, often concealed behind an event horizon. When discussing the universe's start, a singularity takes on a monumental role. The concept of the Big Bang posits that the universe began from an initial singularity around 13.8 billion years ago. This primal singularity is thought to have been a state where all of the universe's mass and energy were concentrated in an infinitely small point. The extreme conditions of this initial singularity mean that our current understanding of physics, particularly general relativity, cannot fully describe the state of the universe at that moment. Quantum mechanics, which governs the behaviors at the smallest scales, similarly struggles to provide a complete picture. Thus, singularities highlight the limitations of our existing theories and serve as focal points for scientific inquiry and theoretical development. They emphasize the need for a new unifying theory, such as quantum gravity, that can reconcile the principles of quantum mechanics with those of general relativity. By studying singularities, scientists aim to unlock the secrets of the universe's origin, hoping to uncover the fundamental laws that govern the earliest moments of existence and continue to influence the cosmos's vast and intricate evolution. Modeling the universe's beginning requires a robust arsenal of mathematical tools, primarily drawn from the fields of general relativity and quantum mechanics, each bringing its unique formalisms to the cosmic table. In general relativity, Einstein's field equations serve as the cornerstone, describing the curvature of spacetime associated with the presence of mass and energy. These equations are pivotal in constructing models of the universe's early state, characterized by extreme densities and gravitational forces. Solutions to these equations, such as the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, describe a homogeneous and isotropic universe which expands from an initial singularity. Complementing this are the tools from quantum mechanics, particularly those involving wave functions and probabilistic descriptions of particles. Quantum field theory extends these principles to fields, offering a framework to understand the behavior of particles under extreme conditions, such as those present shortly after the Big Bang. Techniques like renormalization help manage the infinities that arise in quantum calculations, allowing for more manageable and meaningful results. Moreover, sophisticated algorithms and simulations enable cosmologists to numerically model the complex interactions and evolutions of the early universe. Computational cosmology employs methods such as lattice simulations and n-body simulations to replicate the dynamic, ever-evolving cosmos. These simulations provide insights into phenomena like cosmic inflation, where rapid expansion smoothens and stretches initial quantum fluctuations into the large-scale structures we observe today. Together, these mathematical tools and techniques form the backbone of cosmological models, shedding light on the universe's enigmatic origins and its ongoing evolution. As our mathematical toolkit continues to expand and refine, so too does our understanding of the cosmos, ever inching closer to unraveling the profound mysteries of the universe's birth. Physicists harness the power of computer simulations to study the universe's origin by creating detailed and dynamic models that mimic the conditions and processes thought to have occurred in the early cosmos. These simulations are built upon the foundational principles of both general relativity and quantum mechanics, integrated with advanced computational algorithms to handle the vast arrays of data and complex calculations required. One of the key applications of computer simulations in cosmology is the study of cosmic inflation, a period of rapid expansion that is believed to have occurred fractions of a second after the Big Bang. By inputting initial conditions based on theoretical models, such as the energy density of the early universe and the properties of quantum fields, physicists can simulate the inflationary phase to observe how microscopic quantum fluctuations are stretched to macroscopic scales. These simulations help researchers understand how these initial fluctuations eventually led to the large-scale structures like galaxies and galaxy clusters that populate the universe today. Furthermore, computer simulations are instrumental in modeling the formation and evolution of cosmic structures. Using n-body simulations, which track the interactions between a large number of particles under the influence of gravity, scientists can recreate the assembly of dark matter halos and the subsequent formation of galaxies. These simulations are often run using powerful supercomputers, allowing for high-resolution outputs that offer detailed insights into the processes that govern cosmic development. By comparing the results of these simulations with observational data, such as the cosmic microwave background radiation or the distribution of galaxies, physicists can refine their models and improve their understanding of the universe's evolution. These computational studies are invaluable tools, providing a virtual laboratory in which hypotheses can be tested and theories can be validated, thereby deepening our comprehension of the universe's origin and its complex, ever-changing nature. Several key astronomical observations provide robust support for current theories about the universe's origin, particularly the Big Bang theory. These observations span a range of phenomena and timescales, offering converging lines of evidence that help to piece together the cosmic story. This faint glow of microwave radiation pervades the entire universe and is considered the afterglow of the Big Bang. It represents the residual thermal radiation from the time when the universe cooled enough for photons to decouple from matter, approximately 380,000 years after the Big Bang. The uniformity and slight anisotropies in the CMB provide critical information about the early universe's conditions, supporting the notion of a hot, dense origin followed by expansion. Another pivotal observation is the redshift of distant galaxies, famously noted by Edwin Hubble in the 1920s. Hubble discovered that galaxies are receding from us, with the velocity of their recession proportional to their distance, a finding encapsulated in Hubble's law. This galactic redshift indicates that the universe is expanding, a cornerstone of the Big Bang theory. The observation suggests that galaxies were closer together in the past, pointing to an initial singularity when the universe's expansion began. Additionally, the abundance of light elements such as hydrogen, helium, and traces of lithium provides further confirmation. Predictions made by Big Bang nucleosynthesis, a theory that describes the formation of the universe's earliest elements, match closely with observed concentrations. This agreement supports the concept that these elements were formed within the first few minutes of the universe's existence when temperatures and densities were extremely high. These key observations, along with others like large-scale galaxy distributions and gravitational lensing effects, collectively reinforce the Big Bang theory. They offer a coherent and comprehensive picture of the universe's origin, corroborating theoretical models with empirical data and enhancing our understanding of cosmic evolution. Telescopes and satellites have revolutionized our understanding of the early universe by enabling us to observe and analyze celestial phenomena with unprecedented detail and precision. These sophisticated instruments extend our vision far beyond the limits of the naked eye, capturing light from the most distant and ancient objects, many of which formed shortly after the Big Bang. Space-based observatories like the Hubble Space Telescope and the more recent James Webb Space Telescope play pivotal roles in this endeavor. Positioned above Earth's atmosphere, these telescopes avoid atmospheric distortion and can detect a wider range of wavelengths, from ultraviolet to infrared. The Hubble Space Telescope, for instance, has provided deep field images that reveal thousands of galaxies at various stages of evolution, some appearing as they were over 13 billion years ago. These observations allow scientists to study the formation and development of galaxies, stars, and other cosmic structures during the universe's formative years. In the realm of microwave and radio astronomy, satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have been instrumental in mapping the cosmic microwave background, CMB radiation. These missions have measured the minute temperature fluctuations in the CMB with remarkable accuracy, offering a snapshot of the universe just 380,000 years after the Big Bang. The detailed maps generated by these satellites provide critical insights into the universe's initial conditions, the nature of dark matter and dark energy, and the overall geometry and expansion rate of the cosmos. Additionally, instruments like the Large Hadron Collider, LHC, simulate conditions similar to those of the early universe by colliding particles at extremely high energies, shedding light on fundamental particles and forces that shaped the cosmos. Observatories dedicated to gravitational waves, such as LIGO and Virgo, also contribute to our understanding by detecting ripples in space-time caused by cataclysmic events, offering indirect evidence of processes occurring in the early universe. These telescopes and satellites serve as time machines, peering back into the distant past and unraveling the mysteries of the universe's beginnings. By collecting and analyzing light and other signals from the furthest reaches of space, they help paint a comprehensive picture of how the universe has evolved over billions of years, advancing our knowledge of cosmology and astrophysics. Observing distant galaxies and quasars has provided invaluable insights into the history and evolution of the universe, shedding light on many fundamental aspects of cosmology and astrophysics. These celestial objects, some dating back to the universe's infancy, serve as cosmic time capsules that help us understand the formation and evolution of the cosmos. Distant galaxies, particularly those observed through deep field observations by the Hubble Space Telescope and other large observatories, reveal how structures in the universe have evolved over billions of years. By examining the light from these galaxies, which has traveled for vast periods before reaching us, astronomers can study the formation and growth of galaxies and galaxy clusters. Observations show that galaxies in the earlier universe were often smaller, less structured, and more numerous, frequently undergoing mergers and interactions that contributed to their evolution into the more massive, structured galaxies seen today. These studies also highlight the role of dark matter in galaxy formation and the influence of dark energy in driving cosmic expansion. Quasars, on the other hand, are incredibly luminous objects powered by supermassive black holes at the centers of young, active galaxies. These black holes accrete matter at tremendous rates, emitting copious amounts of radiation across various wavelengths, making quasars some of the most luminous objects in the universe. Observing quasars provides information about the conditions in the early universe, including the growth and evolution of supermassive black holes. The light from quasars often passes through intervening clouds of gas, enabling scientists to study the intergalactic medium's composition and evolution over cosmic time. Moreover, quasars serve as beacons for understanding large-scale structure. Their distribution helps map the universe's vast cosmic web, revealing how matter is distributed on the largest scales. Their light also allows scientists to probe the reionization epoch, a period when the universe's initially neutral gas was ionized by the first stars and galaxies. Distant galaxies and quasars offer a window into the universe's past, illuminating the processes that have shaped the cosmos from the Big Bang to the present day. These observations have significantly enhanced our understanding of galaxy and black hole formation, the role of dark matter and dark energy, and the overall structure and expansion of the universe, deepening our knowledge of the fundamental workings of the cosmos. Detecting and studying cosmic microwave background (CMB) radiation involves a combination of advanced technology and meticulous analysis to glean insights from this faint remnant of the early universe. The CMB is the afterglow of the Big Bang, a nearly uniform radiation field that fills the universe and provides a snapshot of the cosmos approximately 380,000 years after its inception. Key to its detection and study are space-based observatories and finely tuned instrumentation designed to measure microwave radiation with utmost precision. One of the pioneering missions in this field was the Cosmic Background Explorer, COBE, launched in 1989. COBE provided the first detailed measurements of the CMB, confirming its existence and uniformity, and detecting minuscule temperature fluctuations or anisotropies that hint at the initial density variations leading to galaxy formation. These findings were later refined by the Wilkinson Microwave Anisotropy Probe, WMAP, which launched in 2001. WMAP delivered higher resolution maps of the CMB, significantly enhancing our understanding of the universe's age, composition, and curvature. The most sophisticated mission to date has been the Planck satellite, launched by the European Space Agency in 2009. Planck provided even more detailed and sensitive measurements of the CMB, capturing temperature and polarization anisotropies with unprecedented resolution. These detailed maps show tiny variations in temperature and polarization across the sky, which reflect the density fluctuations that eventually led to large-scale structures in the universe. Detecting the CMB requires precise instrumentation capable of isolating the microwave signals from various sources of noise, including those from our own galaxy and the satellite itself. Observatories like COBE, WMAP, and Planck are equipped with microwave radiometers and bolometers, which measure the intensity of microwave radiation across different frequencies. By observing the CMB at multiple frequencies, scientists can differentiate the CMB signal from foreground emissions. Moreover, ground-based and balloon-borne experiments also contribute valuable data. Instruments like the Atacama Cosmology Telescope, ACT, and the South Pole Telescope, SPT, observe the CMB from high-altitude locations, where the atmosphere is thinner, reducing interference. Balloon experiments like Boomerang and Archeops have also provided critical measurements. The detailed analysis of CMB data involves complex algorithms and models to interpret the temperature and polarization patterns. This analysis helps cosmologists infer critical information about the universe's rate of expansion, Hubble constant, the density and composition of matter and energy, and the initial conditions that set the stage for the formation of galaxies and other large-scale structures. In summary, studying the CMB radiation is a cornerstone of cosmology, relying on space-based missions, ground-based observatories, and balloon experiments to capture and analyze the faint microwave signals from the universe's early moments. These observations offer a window into the infancy of the cosmos, providing empirical support for the Big Bang theory and enhancing our understanding of the universe's fundamental properties and evolution. Particle accelerators play a crucial role in understanding the universe's beginnings by replicating the extreme conditions that existed just moments after the Big Bang. These powerful machines accelerate particles to nearly the speed of light and collide them with incredible energy, allowing physicists to probe fundamental forces and particles that governed the early universe. The insights gained from these experiments help us unravel the mysteries of the cosmos and refine our theoretical models. One of the most prominent particle accelerators is the Large Hadron Collider, LHC, at CERN near Geneva. The LHC is the world's largest and most powerful particle accelerator, capable of achieving collision energies up to 13 tera-electron volts. By smashing protons and heavy ions together at these immense energies, the LHC recreates conditions similar to those present microseconds after the Big Bang, providing a unique opportunity to study fundamental particles and interactions, such as the strong and weak nuclear forces. A landmark discovery at the LHC was the Higgs boson in 2012, a particle that confirms the mechanism by which particles acquire mass. The Higgs field, associated with the Higgs boson, is believed to have played a crucial role in the early universe, helping shape the mass of elementary particles and influencing the universe's overall evolution. Discovering and studying the Higgs boson has vastly improved our understanding of the standard model of particle physics, which describes the fundamental particles and interactions. Particle accelerators also enable the study of rare and short-lived particles that were abundant in the early universe, but are not commonly found today. These experiments provide indirect evidence of conditions and processes that occurred during the universe's infancy. For example, the study of quark-gluon plasma, a state of matter that existed microseconds after the Big Bang, is made possible by heavy ion collisions in particle accelerators. This plasma offers insights into the strong nuclear force that binds quarks inside protons and neutrons. Accelerators also facilitate the search for new physics beyond the standard model, such as supersymmetry, extra dimensions, and dark matter candidates. Discovering or ruling out these new theories can significantly impact our understanding of the universe's formation and the fundamental laws that govern it. Additionally, particle accelerators provide data to refine cosmological models and support experiments in particle astrophysics, like those investigating neutrinos, which have crucial implications for the universe's overall mass and energy balance. In summary, particle accelerators are indispensable tools in modern physics, simulating the high-energy environments of the early universe and enabling detailed studies of fundamental particles and forces. The discoveries made through these experiments not only help to validate and refine existing theories, but also open new avenues for understanding the profound questions about the universe's origins and fundamental nature. Studying the universe's origin is fraught with significant challenges, both technological and conceptual. One of the primary difficulties lies in the sheer scale of time and space involved. The events that occurred nearly 13.8 billion years ago are incredibly distant in both temporal and spatial terms. Observing and interpreting signals from that era requires not only advanced technology, but also an understanding that pushes the boundaries of current physics. Telescopes like the James Webb Space Telescope are designed to capture faint light from the early universe. But even these marvels of engineering can only go so far. The farther back in time we look, the fainter and more redshifted the signals become, demanding even more sensitive instruments and innovative methods of data analysis. Moreover, our understanding of the fundamental laws of physics themselves imposes limitations. For instance, the conditions during the Big Bang were extreme, involving energies and densities far beyond what we can reproduce in laboratories on Earth. Theoretical models, such as those provided by quantum mechanics and general relativity, often clash under these extreme conditions, leading to incomplete or conflicting descriptions of the early universe. Physicists seek a unifying theory that can reconcile these differences, but achieving this is one of the most formidable challenges in modern science. Even concepts such as dark matter and dark energy, which constitute a significant portion of the universe, remain largely mysterious and hard to incorporate into a cohesive understanding of the universe's origin. Additionally, interpreting the data we do obtain often requires complex models and simulations, which themselves can rely on assumptions that might one day be proven incorrect. This makes cosmology uniquely iterative. Each new discovery can potentially rewrite significant portions of what we thought we knew. Therefore, the quest to understand the universe's origin is a continually evolving journey, demanding patience, ingenuity, and an open mind willing to embrace the profound complexities of the cosmos. The beginning of the universe is a topic shrouded in both wonder and mystery, with several profound questions remaining unanswered. One of the most fundamental questions is what actually caused the Big Bang. The prevailing theory asserts that the universe expanded from an extremely hot and dense singularity, but the mechanism triggering this event is still unknown. Were there quantum fluctuations in a pre-existing state that led to this massive expansion? Or are there new, not yet discovered principles of physics at play? These questions push us to the very edge of our current understanding and beckon toward new physics that could potentially rewrite our understanding of cosmic origins. Another central enigma pertains to the nature and role of dark matter and dark energy. Observational data indicate that about 85% of the universe's mass energy content is made up of dark matter and dark energy. Yet we have little understanding of what these substances are or how they interact with ordinary matter. Deciphering the true nature of these components could illuminate significant aspects of the universe's beginning and evolution. How did dark matter influence the clumping of cosmic structures in the early universe? What is the role of dark energy in driving the accelerated expansion of the universe, which began billions of years after the Big Bang? These mysterious entities have far-reaching implications for cosmology, challenging us to delve deeper into the unseen and largely unknown aspects of the universe. Furthermore, the quest to unify general relativity and quantum mechanics, often referred to as the search for a theory of everything, remains a monumental unanswered question. Both of these theories are cornerstones of modern physics, but are fundamentally incompatible under the extreme conditions of the early universe. A unified theory could potentially provide insights into the initial conditions of the Big Bang and offer explanations for the nature of space-time itself. Each of these questions represents a frontier in our understanding of the cosmos, reminding us that the universe's beginnings are not just a scientific puzzle, but a profound mystery that continues to inspire human curiosity and ingenuity. Studying the conditions before the Big Bang presents an array of formidable challenges, primarily due to the limitations of our current scientific theories and observational capabilities. First and foremost, the concept of before the Big Bang itself is shrouded in complexity. According to general relativity, time and space as we understand them emerged with the Big Bang. This means that any event or condition before the Big Bang exists outside the realm of conventional time, making it inherently difficult to frame, let alone investigate, within our current scientific paradigms. Our understanding of causality and time is deeply rooted in the fabric of space-time described by relativity, which doesn't provide a framework for events occurring outside of this continuum. Additionally, the realm before the Big Bang is theorized to involve conditions of extreme density and temperature where our established laws of physics, particularly general relativity and quantum mechanics, break down. These two cornerstone theories of modern physics are notoriously incompatible under such extreme conditions. General relativity governs the large-scale structure of space-time, while quantum mechanics describes the behavior of particles at the smallest scales. Yet neither theory can adequately describe the singularity from which the Big Bang is believed to have sprung. This theoretical incompatibility means that a new, yet-to-be-discovered theory of quantum gravity is essential for accurate models of pre-Big Bang conditions. Until such a theory is developed and validated, our understanding remains fragmented and speculative. On the observational front, our primary tool for studying the early universe is electromagnetic radiation, yet this too has its limits. The furthest back we can observe directly is the cosmic microwave background radiation, CMBR, which represents the state of the universe about 380,000 years after the Big Bang, when photons decoupled from matter. Prior to this epoch, the universe was opaque to electromagnetic radiation, rendering direct observations impossible. The lack of direct observational evidence constrains us to infer conditions through theoretical models and indirect measurements, such as gravitational waves or particle interactions, which themselves are still emerging fields of study. Thus, the twin challenges of theoretical limitations and observational constraints make the study of conditions before the Big Bang an intensely difficult but equally fascinating frontier in cosmology. These hurdles inspire the continual refinement of our mathematical models and the development of new technologies, driving the quest to unlock one of the most profound mysteries of our existence. The quest to explore the universe's origin is hampered by several significant technological limitations that pose formidable challenges for cosmologists and physicists. One of the most pressing limitations is the sensitivity and resolution of our observational instruments. Telescopes like the Hubble Space Telescope and the more advanced James Webb Space Telescope provide breathtaking images and valuable data from across the cosmos. However, even these state-of-the-art devices have limitations in detecting extremely faint signals from the early universe. The farther back in time we look, the fainter and more redshifted the signals become, necessitating even more sensitive instruments to capture these elusive photons. Current technology can capture light only up to a certain point, and much of what happened immediately after the Big Bang, let alone before it, remains out of reach. Moreover, our ability to replicate and study conditions akin to those of the early universe in terrestrial laboratories is severely limited. Particle accelerators, like the Large Hadron Collider, LHC, can recreate conditions that existed mere fractions of a second after the Big Bang by accelerating particles to near light speed and colliding them. While these experiments have provided invaluable insights, such as the confirmation of the Higgs boson, they fall short of replicating the extreme conditions closer to the singularity from which the Big Bang emerged. Without the ability to recreate such conditions, our theoretical models remain largely untested at those energy scales. Another critical technological limitation involves the detection and study of dark matter and dark energy, which constitute about 85% of the universe's mass energy content. Current detectors for dark matter, essentially elaborate underground experiments shielded from cosmic rays, have yet to definitively capture a single dark matter particle. Similarly, dark energy, inferred from the accelerated expansion of the universe, remains enigmatic in its actual properties and origins. These unknowns significantly constrain our overall understanding of the universe's origin, as both dark matter and dark energy likely played critical roles in shaping the cosmos. Finally, data processing and computational limitations also play a role. Analyzing massive datasets from observatories and experiments requires immense computational power and sophisticated algorithms. While we have made significant strides in this area, the ever-increasing volume and complexity of data call for continual advancement in computational technologies, including quantum computing, which might one day offer the power needed to model early universe conditions more accurately. Together, these technological constraints form a substantial barrier to fully comprehending the origins of the universe. However, they also serve as catalysts, driving innovation and the continuous improvement of our scientific instruments and methodologies. The pursuit of overcoming these hurdles remains a central inspiration for the scientific community. The concept of nothing is one of the most intriguing and philosophically challenging aspects of cosmology and scientific inquiry. In everyday language, nothing denotes the absence of anything, no matter, no energy, no space, and no time, a true void. However, when scientists approach this concept, especially in the context of the universe's origin, it takes on more nuanced meanings. Firstly, quantum mechanics introduces the idea that even a perfect vacuum, which we might equate with nothing, isn't truly empty. Due to the uncertainty principle, there are always fluctuations at the quantum level, with particle-antiparticle pairs constantly forming and annihilating almost instantaneously. This phenomenon suggests that nothing is an active, dynamic state rather than a static void. These quantum fluctuations provide a basis for understanding how something could indeed emerge from nothing. For instance, certain cosmological models propose that the universe could have arisen from a quantum vacuum fluctuation, a fleeting state of imbalance that ultimately gave rise to everything we observe. Furthermore, the concept of nothing is also addressed in theories related to the multiverse. Here, our universe could be just one of many, each emerging from different vacuums or phases of an overarching multiverse. In this context, what we perceive as nothing in our universe could be part of a much larger, continually fluctuating multidimensional space. In such models, The birth of a universe is a transition from one state of nothingness in a particular dimensional construct to a state of something governed by different physical laws. Cosmologists also explore the idea of nothing within the framework of general relativity and space-time. The inflating universe theory, a widely accepted concept, posits that our universe underwent rapid expansion from an almost inconceivably small, hot and dense singularity. In this view, nothing can be thought of as a state without the dimensions that define our current reality, an absence of the space-time fabric itself. Transitioning from this state to our inflating universe might sound counterintuitive, but it aligns with certain interpretations of how physical laws could operate outside our known space-time continuum. Addressing nothing involves an interdisciplinary effort, combining quantum mechanics, general relativity, and philosophical inquiry. Scientists aren't merely debating semantics, but are constantly pushing the boundaries of theory and experimentation to better grasp this elusive concept. The notion of nothing thus serves as a profound frontier in our quest to understand the very essence of existence and the origins of the universe. The understanding of the universe's origin has far-reaching implications that resonate across various fields of science, providing foundational insights and driving innovation in numerous ways. In the realm of physics, cosmological discoveries continually refine our understanding of fundamental particles and forces. For example, the conditions present during the early universe serve as a natural laboratory for testing the limits of particle physics theories, such as the behavior of the Higgs boson and the characteristics of neutrinos. These insights inform our understanding of how fundamental particles interact and influence the development of new technologies, from medical imaging devices to particle accelerators. In astronomy and astrophysics, the study of the universe's origin sheds light on the life cycles of stars, the formation of galaxies, and the evolution of cosmic structures. By examining the cosmic microwave background radiation, scientists gain insights into the density fluctuations that eventually led to the formation of galaxies and clusters. This understanding not only enriches our knowledge of the universe's vast architecture, but also aids in the identification of potentially habitable exoplanets, advancing the search for extraterrestrial life. The exploration of cosmological origins also intersects meaningfully with the field of chemistry. The distribution and abundance of elements observed in the universe today originated from nucleosynthesis processes that occurred within the first few minutes after the Big Bang and subsequently in the interiors of stars. This knowledge helps chemists understand the atomic building blocks that compose matter, influencing everything from the development of new materials to the comprehension of biochemical processes essential for life. Moreover, the principles derived from cosmology have practical applications in the field of engineering. Techniques used to measure cosmic distances and map the universe's structure, such as the Doppler effect and spectroscopy, find utility in developing advanced navigation systems and improving precision in various engineering disciplines. The technological advancements required to observe and analyze distant cosmic phenomena often spur innovations that have ripple effects across industries, boosting computational methods, data handling, and imaging technologies. On a more abstract level, studying the universe's origin enriches philosophical and existential inquiries. It influences the fields of anthropology and sociology by shaping our understanding of humanity's place in the cosmos. This broader perspective impacts ethical considerations in science and technology, prompting discussions about the long-term sustainability of human civilization and our responsibilities as stewards of Earth and the cosmos. Thus, the pursuit of understanding the universe's origin is not insular, but rather a catalyst that drives progress and innovation across a spectrum of scientific disciplines, enriching both our theoretical frameworks and practical capabilities. The origin of the universe provides profound insights into the nature of time and space that challenge our everyday intuitions and extend the boundaries of our understanding. According to the Big Bang theory, time and space themselves began with the singularity from which the universe expanded. This implies that the universe didn't just emerge within pre-existing time and space, but that time and space themselves are dynamic entities that began and have been evolving since the Big Bang. This notion fundamentally alters our conventional perspective, suggesting that time and space are intertwined constructs, components of the fabric of the cosmos described by the theory of general relativity. In this framework, time is not an absolute, unchanging backdrop against which events occur. Instead, it flows and warps in response to the presence of mass and energy. This is most famously exemplified by the concept of space-time curvature, where massive objects like stars and planets deform the space-time around them, affecting how time is experienced in those regions. Observations, such as the gravitational time dilation experienced near black holes, underscore the malleable nature of time and space, following the principles set out by Einstein's equations. Moreover, the early universe was governed by conditions so extreme that our familiar laws of physics break down when approaching the singularity at t=0. This period, often referred to as the Planck epoch, makes clear that the conventional understanding of time as a continuous linear progression may not apply under such conditions. Instead, time at those scales could potentially be quantized or have different properties altogether, perhaps described by a future theory of quantum gravity that successfully merges quantum mechanics with general relativity. Concepts like discrete time or loop quantum gravity are ongoing areas of theoretical research, aiming to shed light on time's fundamental nature in the context of the universe's birth. Additionally, the expansion of the universe, driven by dark energy, offers further clues about the interplay of time and space. The accelerating expansion suggests that space itself is stretching, carrying galaxies away from each other over time. This dynamic expansion impacts how we understand distances and the passage of time on cosmic scales. As space expands, the light traveling through space also stretches, which leads to the redshift observed in distant galaxies. This expanding universe paints a picture where space is an active participant in the cosmos's evolution rather than a static backdrop. Thus, the study of the universe's origin indicates that time and space are far from being fixed and immutable. Instead, they are dynamic, interwoven entities that have evolved alongside the universe, offering an ever-deepening puzzle that continues to inspire scientific and philosophical inquiry. Understanding these complex, elastic qualities of time and space brings us closer to grasping the true nature of the cosmos and our place within it. The study of the universe's beginning profoundly influences our understanding of reality by challenging and expanding our conceptual frameworks. By examining the origins of the cosmos, we confront foundational questions about the nature of existence itself, pushing the boundaries of what we consider to be the real world. This inquiry doesn't merely add to our accumulation of knowledge, but often redefines the very parameters by which we understand reality. At the simplest level, the realization that time and space had a beginning with the Big Bang fundamentally alters our perception of existence. We are conditioned to think of time as a linear continuum stretching infinitely into the past and future. However, the scientific evidence suggesting that time itself began nearly 13.8 billion years ago calls for a re-evaluation of these intuitions. This discovery necessitates a new conceptual framework where time and space are dynamic and intertwined entities, components of an evolving, expanding universe. Additionally, the principles of quantum mechanics, which govern the behavior of particles on the smallest scales, have revolutionized our understanding of reality at the most fundamental level. Quantum phenomena such as superposition and entanglement defy common sense and classical intuition. They suggest that particles can exist in multiple states simultaneously and can be instantaneously correlated across vast distances. Such principles not only challenge our notions of causality and locality, but also open up philosophical debates about the nature of reality itself. The implications of quantum mechanics are far-reaching, suggesting that our macroscopic reality is deeply rooted in probabilistic and interconnected processes that are not immediately observable. The study of cosmic origins also introduces us to the perplexing concepts of dark matter and dark energy, which make up approximately 85% of the universe's mass energy content. These unseen components challenge the completeness of our current scientific models and suggest that our visible, tangible reality is just a small fraction of what truly exists. Understanding these dark components could fundamentally alter our grasp of the universe, from the formation of structures to the ultimate fate of the cosmos. Moreover, Insights from cosmology influence our philosophical and existential views, including questions about human significance and the nature of existence. The realization that the universe has a history, an evolution, and possibly a finite future compels us to rethink our place within it. Are we part of a grand cosmic plan, or merely the result of random processes in an indifferent universe? These questions, prompted by our study of the cosmos, resonate deeply across disciplines, from philosophy to theology to ethics, influencing our collective worldview. In conclusion, the study of the universe's beginning is not just a scientific endeavor. It is an intellectual and philosophical journey that reshapes our understanding of reality. By challenging our core assumptions and expanding the boundaries of what we consider possible, it enriches our perception of the cosmos and our place within it, offering profound insights into the nature of existence itself. The implications for the future of the universe are vast and inherently linked to the fundamental properties and dynamics that govern cosmic evolution. One of the most compelling scenarios revolves around the role of dark energy, a mysterious force that is driving the accelerated expansion of the universe. If dark energy remains constant, this expansion will continue indefinitely, leading to a scenario known as the Big Freeze or heat death. In such a future, galaxies will drift ever farther apart. Stars will exhaust their nuclear fuel and die out, and the universe will gradually become a cold, dark, and desolate place. Over immense timescales, even black holes would evaporate through Hawking radiation, leaving behind a dilute soup of particles in an ever-expanding void. A more drastic variant of this scenario is the Big Rip. If the strength of dark energy increases over time, it could eventually overpower all other forces, tearing apart galaxies, stars, planets, and eventually the very fabric of space-time. This would result in a catastrophic end where all structures in the universe disintegrate. Though this scenario is less likely according to current observations, it remains a topic of theoretical interest and investigation. On the other hand, another possibility proposed by some models is the Big Crunch. In this scenario, if the density of the universe is high enough, the gravitational attraction of all matter could eventually halt the current expansion and reverse it. This would lead to a cosmic contraction, with galaxies rushing back together, stars colliding, and temperatures rising dramatically. Ultimately, the universe could collapse back into a hot, dense state, potentially leading to conditions similar to those at the universe's birth. Some speculative theories even suggest that such a collapse could trigger another Big Bang, giving rise to a cyclical model of the universe where epochs of expansion and contraction follow one another indefinitely. Additionally, concepts like the multiverse add another layer of complexity to our understanding of the universe's future. If our universe is just one of many, then its demise might be a localized event within a much grander and possibly eternal multiversal framework. This perspective shifts the focus from a single universe's fate to a broader context in which the birth and death of individual universes are part of an ongoing process. Understanding the universe's ultimate fate also has philosophical and existential implications. It prompts us to consider the long-term prospects for life and intelligence. If the universe is heading toward a cold, dark demise, the challenge for advanced civilizations would be to find ways to survive and thrive in an increasingly inhospitable cosmic environment. This could involve harnessing new forms of energy, altering cosmic trajectories, or even finding ways to transition into other universes, should the multiverse theory hold true. The implications for the future of the universe encompass a range of scientifically speculative scenarios, each with profound consequences for our understanding of cosmic evolution and the ultimate fate of all matter, energy, and life within it. These diverse possibilities continue to drive scientific investigation, philosophical contemplation, and imaginative explorations about the nature and destiny of our cosmos. The concept of a universe emerging from nothing profoundly influences our philosophical views by challenging and potentially transforming our understanding of existence, causality, and creation. This idea intersects with both metaphysical inquiries and practical everyday notions of reality, prompting a re-examination of some of the most fundamental questions that humanity has pondered. Firstly, the notion that the universe could arise from nothing profoundly impacts our understanding of causality. Traditionally, causes are thought to precede effects within the framework of time and space. However, if the universe itself, a vast, intricate system of matter, energy, and space-time, emerged from a state we describe as nothing, it forces us to reconsider what we mean by causality. In this context, nothing might not be a simple void, but a quantum vacuum brimming with potential, as quantum theory suggests. This shifts our understanding of causality from a linear, deterministic chain of events to a more complex, probabilistic framework where quantum fluctuations can give rise to entire universes. This idea touches on existential and epistemological questions as well. If the universe sprang into being from a quantum fluctuation or similar process, it challenges the notion of a purposeful creation. This bears heavily on traditional religious and metaphysical narratives that posit a creator or an initial cause. It raises questions about the necessity of a first cause or a prime mover, suggesting instead that the universe might be a spontaneous, natural occurrence. This can lead to a more secular worldview where the cosmos is seen as a magnificent and intricate system that operates according to natural laws without needing an external agent to initiate its existence. The concept of a universe from nothing invites reflection on the nature of existence itself. What does it mean for something to exist, and how do we comprehend the transition from non-existence to existence? This touches on deep metaphysical issues about the definition and nature of nothing. If nothing includes quantum fluctuations, it suggests that nothingness is not an empty void but a fertile ground for the potential emergence of universes. This redefines our understanding of potentiality and actuality, providing a fertile ground for new philosophical discourse. The idea also has implications for our sense of purpose and place in the cosmos. On one hand, it can induce a sense of existential vertigo, a feeling of insignificance in a universe that appears spontaneously and may end similarly without inherent purpose. On the other hand, it might inspire awe and wonder about the self-organizing principles of nature, fostering a sense of connection to a cosmos that follows intricate and beautiful laws, even if devoid of any overarching purpose. This concept encourages interdisciplinary dialogues, blending philosophy, metaphysics, and science. It prompts philosophers to consider scientific insights in their metaphysical frameworks and encourages scientists to engage with philosophical questions of existence and causality. This interdisciplinary approach enriches both fields, fostering a holistic understanding of our place in the universe. The concept of a universe from nothing challenges our traditional notions of causality, existence, and purpose. It offers a paradigm shift that encourages new ways of thinking about the origins and nature of reality, inviting a deep philosophical inquiry that complements scientific exploration. The field of cosmology is constantly evolving, with recent discoveries shedding new light on the universe's origin and its earliest moments. One of the most groundbreaking advancements in recent years involves the observations made by the James Webb Space Telescope, JWST, which was launched in December of 2021. The JWST is providing unprecedented insights into the early universe, enabling astronomers to peer back farther than ever before to within a few 100 million years after the Big Bang. The telescope's infrared capabilities allow it to capture light from the first galaxies that formed, helping scientists understand how these early structures evolved and interacted in the nascent universe. Another significant discovery relates to the cosmic microwave background radiation, CMBR, the faint afterglow left over from the Big Bang. Enhanced measurements from missions like the Planck satellite have provided the most detailed map of the CMBR to date. These measurements offer crucial information about the universe's initial conditions, including the distribution of matter and energy moments after the Big Bang. By refining the parameters of the standard cosmological model, these observations help to address fundamental questions about the universe's overall shape, density, and expansion rate. Additionally, the detection and study of gravitational waves have opened a new frontier in cosmology. First directly observed in 2015 by the LIGO and Virgo collaborations, gravitational waves provide a new way to observe the universe. These ripples in space-time are produced by cataclysmic events, like the collisions of black holes and neutron stars. The study of these waves offers insights into the behavior of matter and energy under extreme conditions, potentially revealing new aspects of the early universe that are not accessible through electromagnetic observations alone. Future gravitational wave observatories, such as LISA, Laser Interferometer Space Antenna, promise to further enhance our understanding by detecting waves from even earlier in the universe's history. Dark matter and dark energy remain two of the most enigmatic components of the universe, and recent efforts have focused on understanding their nature and impact on cosmic evolution. While dark matter has not yet been directly observed, its effects are inferred through its gravitational influence on visible matter. Ongoing experiments aim to detect dark matter particles directly, using highly sensitive detectors placed deep underground to shield them from cosmic radiation. Meanwhile, the study of dark energy, which is responsible for the accelerating expansion of the universe, continues to be a primary focus. Observations from the Dark Energy Survey, DES, and upcoming missions like the Euclid spacecraft aim to map the distribution of galaxies and trace the influence of dark energy across cosmic time. Finally, advances in theoretical physics, particularly in the realms of string theory and quantum gravity, continue to push the boundaries of our understanding of the universe's origin. Concepts such as the multiverse and higher dimensional theories offer tantalizing possibilities, though they remain speculative without direct experimental or observational evidence. Researchers are working to unify general relativity and quantum mechanics, potentially leading to a more comprehensive theory that can describe the universe's initial conditions and the true nature of space-time. In summary, recent discoveries in cosmology are transforming our understanding of the universe's origin. Advanced telescopes like the James Webb Space Telescope, precise measurements of the cosmic microwave background radiation, gravitational wave astronomy, and ongoing investigations into dark matter and dark energy are collectively painting a more detailed and nuanced picture of the early cosmos. These efforts continue to push the boundaries of what we know and inspire new questions about the fundamental nature of reality. The quest to understand the universe's beginning drives the development of cutting-edge technologies designed to probe the depths of cosmic history with ever greater precision and sophistication. Among these emerging tools and platforms, several stand out for their potential to revolutionize our comprehension of the universe's origins. The James Webb Space Telescope, JWST, which launched in December of 2021, represents one of the most significant technological advancements. With its highly sensitive infrared instruments, JWST allows astronomers to observe the faint light from the first galaxies and stars formed after the Big Bang. This capability is crucial for studying the early universe because infrared light from these distant objects has been redshifted into longer wavelengths due to the universe's expansion. As a result, JWST will help us understand how the first cosmic structures formed and evolved, providing a clearer picture of the universe's infancy. In addition to space telescopes, ground-based observatories are undergoing significant advancements. For instance, the Extremely Large Telescope, ELT, currently under construction in Chile, will be the world's largest optical and infrared telescope. With a primary mirror spanning nearly 40 meters, the ELT will provide unprecedented resolution and sensitivity, enabling it to observe the earliest galaxies, star clusters, and other cosmic phenomena with remarkable detail. This powerful instrument will complement space-based observations, offering different perspectives on the universe's formative periods. Gravitational wave astronomy is another rapidly advancing field, opening new windows onto the universe's violent and energetic events. Current observatories like LIGO and Virgo have already detected gravitational waves from black hole and neutron star mergers, but future projects promise to push this frontier further. The Laser Interferometer Space Antenna, LISA, an upcoming space-based gravitational wave observatory, will be capable of detecting waves with much longer wavelengths than ground-based detectors. This will allow LISA to observe mergers of supermassive black holes and potentially even primordial gravitational waves, offering insights into conditions fractions of a second after the Big Bang. Technologies specifically designed to detect and study dark matter are also advancing. Experiments such as the Xenon 1T and its successors employ highly sensitive detectors placed deep underground to shield them from cosmic radiation. These experiments aim to capture rare interactions between dark matter particles and ordinary matter. Meanwhile, upcoming projects like the Large Synoptic Survey Telescope, LSST, now known as the Vera C. Rubin Observatory, will map the distribution of dark matter across the universe by observing gravitational lensing effects, helping to elucidate its role in cosmic structure formation. On the theoretical front, advancements in computational technologies and simulations are crucial for modeling the early universe. High-performance computing enables scientists to simulate complex processes such as cosmic inflation, the behavior of quantum fluctuations, and the formation of the first galaxies. These simulations help researchers test and refine their theories, providing a more comprehensive understanding of the conditions that gave rise to the universe as we know it. Furthermore, quantum computing holds promise for revolutionizing our approach to cosmological problems. Quantum computers could potentially simulate aspects of the early universe that are currently intractable with classical computers, offering new avenues for exploring quantum gravity and other foundational physics concepts. One of the most prominent examples of successful international collaboration is the European Space Agency's, ESA, involvement with the James Webb Space Telescope, JWST. While NASA is the primary operator of JWST, the ESA and the Canadian Space Agency, CSA, have contributed significant hardware, scientific instruments, and expertise. This multinational effort has enriched the telescope's capabilities, enabling it to peer into the early universe with unprecedented clarity. By sharing the technological and financial burdens, international collaborations make such ambitious projects feasible and more comprehensive in their scientific scope. Another outstanding example is the Planck satellite, a mission conducted by the ESA with contributions from NASA and various European institutions. The Planck mission has provided the most detailed map of the cosmic microwave background radiation, CMBR, to date, offering crucial insights into the universe's conditions shortly after the Big Bang. The collaboration brought together scientists, engineers, and funding from across Europe and North America, culminating in a dataset that continues to shape our understanding of cosmological parameters and early universe physics. Ground-based observatories like the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, highlight further international cooperation. ALMA is a partnership involving the European Southern Observatory, ESO, the National Radio Astronomy Observatory, NRAO, in the United States, and the National Astronomical Observatory of Japan, NAOJ. This collaboration has created one of the most powerful millimeter-submillimeter telescopes in the world. ALMA's capabilities have been crucial for observing the cold, distant universe, including the gas clouds where the first stars and galaxies formed. In the realm of gravitational wave detection, the collaboration between LIGO, Laser Interferometer Gravitational Wave Observatory, in the United States and Virgo in Europe has been pivotal. Their joint observations have confirmed the existence of gravitational waves, thus opening a new frontier in astronomy. These discoveries provide insights into extreme cosmic events and conditions, indirectly shedding light on aspects of the universe's early moments and the underlying physics. Future collaborations, such as the European Space Agency's LISA, Laser Interferometer Space Antenna, promise to further advance this field by detecting gravitational waves from even more distant and ancient cosmic events. The Large Hadron Collider, LHC, at CERN, the European Organization for Nuclear Research, epitomizes international scientific cooperation in particle physics. Located on the border between France and Switzerland, the LHC is an enormous collaborative project involving thousands of scientists and engineers from over 100 countries. The discoveries made at CERN, such as the identification of the Higgs boson, have significant implications for understanding the fundamental particles and forces that shaped the early universe. These international efforts also extend to theoretical and computational physics. Projects like the Simons Observatory in Chile, aimed at studying the CMBR, are cooperative ventures involving institutions from multiple countries, including the United States, the United Kingdom, and Chile. These collaborations leverage diverse expertise and computational resources, facilitating more sophisticated models and simulations of the early universe. Moreover, international science organizations such as the United Nations Office for Outer Space Affairs, UNOOSA, and the International Astronomical Union, IAU, play critical roles in fostering global cooperation, standardizing data protocols, and ensuring the open exchange of information and resources. In conclusion, international collaborations are pivotal in advancing our understanding of the universe's origin. By combining technological resources, diverse expertise, and financial investment from multiple countries. These collaborative efforts enable the execution of large-scale, ambitious projects that no single nation could undertake alone. This cooperative spirit not only enhances scientific productivity, but also strengthens global ties, leveraging the collective human endeavor to explore the deepest mysteries of our universe. One of the most ambitious missions planned for the near future is the James Webb Space Telescope, often heralded as the successor to the Hubble Space Telescope. Scheduled for launch, the James Webb is designed to peer further into space, and therefore further back in time, than any telescope before it. Its infrared capabilities will allow it to see through cosmic dust clouds that obscure many of the universe's earliest stars and galaxies. Scientists believe this will bring us closer to observing the universe as it existed approximately 13.5 billion years ago, right after the Big Bang. Another fascinating aspect of the James Webb is its ability to study the atmospheres of exoplanets, offering us potential insights into planets that might harbor life, thus linking cosmology with the ever-intriguing search for extraterrestrial intelligence. In another exciting development, the European Space Agency's Euclid mission aims to explore the dark universe, particularly dark matter and dark energy, which constitute about 95% of the total mass energy content of the universe. Utilizing a combination of visible and near-infrared instruments, Euclid will map the three-dimensional distribution of billions of galaxies over more than 1/3 of the sky. By doing so, it will help scientists understand how dark energy influences the expansion of the universe and how dark matter holds galaxies together. Unlike previous telescopes, Euclid's wide-field survey will cover an unprecedented volume of the cosmos, offering a broad perspective that complements the deep, narrow-focused views provided by the James Webb Space Telescope. The insights garnered from Euclid could fundamentally alter our comprehension of the universe's composition and its ultimate fate. In recent years, new theories have emerged that could potentially shake the very foundations of our understanding of the universe's beginning. One such compelling idea is the concept of a quantum bounce, which challenges the traditional Big Bang theory. According to this theory, rather than the universe originating from a singular, infinitely dense point that exploded outward, the universe could have existed in a previous state of contraction. Upon reaching a point of minimum contraction, quantum gravitational effects could have caused a bounce, leading to the current expanding universe. This theory, rooted in loop quantum gravity, offers an intriguing alternative to the notion of a singular beginning, suggesting instead that the universe undergoes endless cycles of expansion and contraction. If proven true, this could imply that the universe is much older than the currently accepted age of approximately 13.8 billion years, and it would reshape our understanding of the universe's life cycle. Another groundbreaking theory is the multiverse hypothesis, which posits that our universe is just one of many, perhaps an infinite number, of universes that exist. This idea stems from string theory and the inflationary model of cosmology. In the inflationary model, the rapid expansion of space right after the Big Bang could have produced bubble universes, each governed by different physical laws and constants. These parallel universes might exist in dimensions beyond our observable reality, making them incredibly difficult to detect with current technology. However, if evidence for the multiverse theory were to emerge, it would revolutionize cosmology by suggesting that what we have observed is only a tiny fraction of a much larger, more complex reality. Our universe's origin, then, would be just one chapter in a far grander, possibly infinite cosmic epic. Leading cosmologists have diverse and sometimes competing views on the universe's origin, reflecting the dynamic and evolving nature of the field. Many still adhere to the Big Bang theory, which posits that the universe began approximately 13.8 billion years ago from an incredibly hot and dense singularity. This theory provides a robust framework that explains the observable expansion of the universe, the cosmic microwave background radiation, and the distribution of elements. However, even those who support the Big Bang theory often acknowledge that it leaves many questions unanswered, particularly regarding what happened before the Big Bang or what caused it. Some of the prominent cosmologists like Stephen Hawking and Roger Penrose in their earlier works have speculated whether time itself began with the Big Bang, making any before question inherently meaningless within our current understanding of physics. Others, like Sir Martin Rees and Alan Guth, have delved deeper into theories that extend or modify the Big Bang model. Alan Guth, for instance, is a leading proponent of the inflationary universe theory, which suggests that a rapid exponential expansion occurred fractions of a second after the Big Bang. This inflationary period could explain some of the universe's large-scale uniformity and structure. Meanwhile, Sir Martin Rees has explored the possibility of a multiverse, suggesting that our universe could be one of many, each potentially with its own unique physical laws. Renowned cosmologist Lisa Randall has also contributed to the dialogue with her ideas on extra dimensions, proposing that the universe might have dimensions beyond the familiar three of space and one of time, which could radically alter our understanding of the cosmos. Overall, while the Big Bang theory remains a cornerstone, leading cosmologists are actively exploring theories that could expand or even revolutionize our comprehension of the universe's ultimate origin. Quantum physicists have offered some thought-provoking perspectives on the concept of a universe arising from nothing. A central idea in this discourse is the notion of quantum fluctuations, which are temporary changes in energy that occur spontaneously in empty space due to the principles of quantum mechanics. According to this view, these fluctuations could generate particles and antiparticles, essentially leading to the creation of matter from an initial state that lacks any material substance. Renowned physicist Lawrence Krauss has popularized this idea, arguing that the laws of quantum mechanics allow for the spontaneous generation of a universe. Krauss suggests that the energy contained within these vacuum fluctuations could provide the seed for the universe, making a cosmos from nothing a physically feasible scenario. Furthering this viewpoint, some quantum physicists draw upon the concept of the multiverse in association with the inflationary theory. According to this framework, the universe might be just one bubble among many in a vast multiverse, with each bubble potentially emerging from quantum fluctuations in different regions of space. This mechanism could eliminate the need for a singular, well-defined initial condition, as proposed by the traditional Big Bang theory. Instead, it portrays a landscape in which spatial regions continually fluctuate, produce energy, and inflate into new universes. This perspective aligns with the principles of quantum field theory, revealing a complex and elegant universe emerging from the inherent properties of the vacuum itself. By delving into these innovative concepts, quantum physicists are drastically broadening our understanding of how a universe could manifest from nothing, challenging traditional ideas and opening new pathways for scientific exploration. Astronomers have long been at the forefront of unraveling the mysteries of the early universe, providing crucial insights into its formative stages. One of the most groundbreaking observations comes from the study of the cosmic microwave background radiation, often described as the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint radiation permeates the universe and serves as a snapshot of the cosmos when it was just 380,000 years old. By analyzing slight temperature fluctuations in the cosmic microwave background, astronomers have been able to infer the distribution of matter and energy in the young universe, offering a window into its structure and composition during its nascent stages. These studies have confirmed the standard model of cosmology, providing strong evidence for the Big Bang theory and subsequent inflationary period. Another significant area of astronomical research focuses on the formation and evolution of the first galaxies and stars, often referred to as cosmic dawn. Utilizing powerful telescopes, such as the Hubble Space Telescope and soon the James Webb Space Telescope, astronomers aim to observe these ancient celestial bodies that formed between a few 100 million and 1 billion years after the Big Bang. These early structures played a vital role in reionizing the universe, a process that made the universe transparent to ultraviolet light and marked the end of the so-called cosmic dark ages. By examining the light from these distant galaxies and stars, astronomers can decode clues about the physical conditions, chemical compositions, and processes that governed the early universe. Such observations not only enhance our understanding of cosmological evolution, but also offer profound implications for our comprehension of how the galaxies and larger-scale structures we observe today came into existence. Philosophers approach the concept of the universe arising from nothing with a blend of curiosity and skepticism, often delving into the metaphysical and existential implications of such an idea. Traditional philosophy has long grappled with the concept of nothingness, considering it not merely as a physical vacuum, but as a profound state devoid of any properties or entities. From this perspective, the notion that the universe could emerge from absolute nothingness challenges the principle of sufficient reason, which posits that everything must have a cause or explanation. Renowned philosopher Martin Heidegger famously pondered, "Why is there something rather than nothing?" This question encapsulates the philosophical intrigue and difficulty in comprehending how a universe could originate without an underlying cause or pre-existing conditions. Contemporary philosophers often engage with scientific ideas to address this conundrum. For instance, philosopher of science Alexander Vilenkin has argued, in alignment with some quantum physicists, that quantum mechanics may provide a framework for understanding the universe's emergence from a quantum vacuum, a sort of nothing that contains potentiality within the laws of physics. Yet, this interpretation prompts further philosophical debate. If this nothing has inherent properties and laws, is it truly nothing? Philosophers like David Albert critique such scientific explanations, arguing that a quantum vacuum is far from the absolute nothingness that classical metaphysics contemplates. Instead, Albert suggests, these scientific models point to a different kind of existence prior to the universe, one with its own complexities and subtleties. The dialogue between philosophy and science enriches our understanding by exploring the boundaries of existence and non-existence. Philosophers question not only the origins of physical reality, but also the frameworks we use to interpret those origins, pushing us to consider deeper questions about causality, existence, and the nature of reality itself. Whether they lean towards metaphysical principles or engage with contemporary scientific theories, philosophers offer a critical lens through which we can examine the profound idea of the universe starting from nothing, underscoring the confluence and sometimes the tension between scientific inquiry and philosophical reflection. Theologians have long contemplated the origins of the universe, often framing their understandings within the context of divine creation. In many religious traditions, the idea of the universe having a beginning is closely tied to the notion of a creator who brought all things into existence. For instance, in the Judeo-Christian tradition, the book of Genesis describes God creating the heavens and the earth from formless void, asserting a deliberate act of creation. This theistic perspective sees the universe's beginning as a purposeful event orchestrated by a divine being, imbuing the cosmos with intentionality and meaning. Islamic theology similarly holds that the universe was created by Allah, who initiated its existence through a divine command. The Quran speaks of Allah's creative power and the orderly nature of the cosmos, emphasizing that the universe is a reflection of divine will. Hindu cosmology, complex and varied, encompasses cycles of creation and destruction, wherein Brahma, the creator god, brings forth the universe. It is sustained by Vishnu and ultimately destroyed by Shiva, only to begin anew. This notion reflects an ongoing, eternal process, rather than a singular beginning. Modern theologians often seek to reconcile these traditional views with contemporary scientific understanding. Some view the Big Bang theory and other cosmological models as complementary rather than contradictory to their religious beliefs. They may see the Big Bang as the method through which a divine creator brought the universe into existence, thus integrating scientific insights with theological doctrine. Figures like Pope John Paul II, for example, have acknowledged the Big Bang theory, suggesting that it does not conflict with the notion of divine creation, but rather describes the process through which God's creative act manifested. In contrast, some theologians engage in more abstract considerations, reflecting upon the metaphysical implications of a universe with a beginning. They contemplate the existential questions such as why there is anything at all rather than nothing, and what implications this has for human existence and the nature of the divine. These perspectives often emphasize the mystery and wonder associated with the universe's origin, inspiring a sense of awe that transcends the purely physical explanations of cosmology. Overall, Theologians bring a rich and multifaceted approach to the discussion of the universe's beginning, blending scriptural interpretations, doctrinal beliefs, and philosophical reflections. They contribute to the broader dialogue by offering perspectives that imbue the cosmos with purpose and meaning, intersecting with yet distinct from the frameworks provided by science and philosophy. Visually representing the Big Bang and the early universe is a challenging yet fascinating endeavor, as it requires translating complex scientific concepts into accessible and engaging images. One of the most iconic visualizations is the depiction of the Big Bang as a colossal explosion, though in reality, it's more accurate to describe it as a rapid expansion of space itself. Artists often illustrate this moment as a bright, intense flash of light emanating from a singular point, with energy and matter spreading outward in all directions. This can help convey the idea of the universe not exploding into pre-existing space, but rather space itself expanding. To portray the early universe, scientists frequently use detailed, color-coded maps created from data gathered by satellites such as the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP. These maps show the cosmic microwave background radiation, the remnant heat from the Big Bang, depicting it as a speckled, multicolored pattern. The variations in color on these maps represent tiny fluctuations in temperature, which correspond to the density variations in the early universe. These density fluctuations eventually led to the formation of galaxies and large-scale structures. By translating minute temperature differences into visual cues, these maps give us a comprehensive view of the universe when it was just 380,000 years old, showcasing the seeds of cosmic structure formation. Further illustrations often employ timelines that stretch from the Big Bang to the present day, segmenting key periods such as inflation, the formation of the first atoms, the cosmic dark ages, and reionization. These timelines help contextualize the major evolutionary phases of the universe, creating a visual narrative that elucidates the complex timeline. Additionally, three-dimensional simulations and animations are invaluable, showing how primordial fluctuations grew into galaxies, clusters, and superclusters under the influence of gravity. Advanced computer visualizations can even simulate the light traveling through these structures, providing dynamic, immersive experiences that draw viewers into the intricacies of the cosmos. Combining artistic creativity with scientific accuracy, these visualizations not only make the Big Bang and the early universe more comprehensible, but also inspire wonder and curiosity. They transform abstract theories and mathematical models into tangible images, bridging the gap between advanced cosmological research and public understanding. Animation plays a pivotal role in explaining complex cosmological concepts, making the abstract and often counterintuitive ideas of cosmology more accessible and understandable to a broader audience. One of the key strengths of animation is its ability to visually simulate processes and phenomena that are either too vast, too small, or occur over timelines far beyond human experience. For example, the concept of cosmic inflation, a phase of rapid expansion a fraction of a second after the Big Bang, can be challenging to grasp through text alone. An animation can vividly depict this expansion, showing how a tiny, dense point balloons outward exponentially, helping viewers to visually apprehend the scale and speed of the process. Animations also excel in illustrating the dynamic nature of astronomical objects and their interactions. For instance, the formation and evolution of galaxies over billions of years can be condensed into a short, visually engaging sequence, showing how initial density fluctuations in the early universe collapse under gravity to form stars and galaxies. This allows viewers to witness cosmic evolution in a way that static images or written descriptions could never fully capture. Similarly, phenomena such as black hole mergers or the bending of light by gravity, gravitational lensing, can be brought to life through high-fidelity animations, providing clear and impactful demonstrations of complex theories. Another significant role of animation in cosmology is in visualizing concepts that are inherently abstract or exist beyond the capabilities of current observational technology. Consider the multiverse theory, which posits the existence of multiple universes with different physical laws. Although we cannot observe these other universes, animations can creatively illustrate how different regions of space might behave under varying conditions, making the idea more tangible. Additionally, animations can demystify the behavior of particles in the quantum realm, showing how quantum fluctuations might give rise to a new universe, bridging the gap between quantum mechanics and cosmology. Educationally, animations are an invaluable tool for teaching challenging topics. They offer a step-by-step breakdown of complex ideas, often combining narration with visuals to reinforce learning. Reputable science organizations and media such as NASA, the European Space Agency, ESA, and educational platforms like Khan Academy frequently use animations in their content to explain phenomena ranging from the life cycle of stars to the expansion of the universe. By transforming intricate scientific data and theories into captivating visual stories, animations not only enhance comprehension but also stimulate interest and curiosity, making the universe's wonders more accessible to all. Overall, the role of animation is indispensable in the realm of cosmology, providing a bridge between sophisticated scientific concepts and the general public's understanding, thereby fostering a deeper appreciation of the cosmos. Artists and scientists often engage in a synergistic collaboration to visualize the universe's origin, blending rigorous scientific data with creative interpretation to craft compelling and accurate representations of cosmological phenomena. This partnership typically begins with scientists providing the foundational knowledge, data, mathematical models, and theoretical frameworks that underpin our understanding of the universe's beginnings. For instance, data from telescopes such as the Hubble Space Telescope, the cosmic microwave background observations, and computer-simulated models of the Big Bang and cosmic inflation serve as the raw materials that artists work with. Artists, in turn, leverage their skills in visual communication, translating these abstract and complex scientific concepts into engaging visuals that are both informative and aesthetically pleasing. This process often involves a deep collaboration where scientists explain the nuances of their data and theories, ensuring that the artistic interpretations are scientifically accurate. For example, artists might create detailed maps of the cosmic microwave background radiation by interpreting data provided by researchers, meticulously ensuring that variations in temperature and density are portrayed correctly. The use of sophisticated computer graphics and animation software has become a critical tool in this collaborative process. Artists can generate high-resolution simulations and animations that depict events such as the Big Bang, the rapid inflation of the early universe, and the formation of the first stars and galaxies. These visualizations are often iterative, with scientists providing feedback at each stage to refine the accuracy and clarity of the images or animations. One exemplary collaboration is the work involved in creating visualizations for planetarium shows or educational documentaries. Scientists might describe the initial conditions of the universe, while artists bring these descriptions to life through immersive 360-degree animations that transport viewers to the very moments after the Big Bang. Shows like these can include dramatic presentations of cosmic events, such as the coalescing of primordial gas into the first stars, the formation of galaxies, and the large-scale structure of the universe, all while staying true to the scientific narrative. Moreover, these interdisciplinary endeavors sometimes result in innovative visual and educational resources, such as interactive apps or virtual reality experiences. For instance, VR headsets can give users a first-hand experience of traveling back in time to witness the universe's origin, providing a tangible sense of scale and dynamism that static images simply cannot offer. By melding the analytical precision of science with the evocative power of art, these collaborations not only enrich our understanding of the universe's origin, but also make it more accessible and engaging to the general public. Whether through a stunning visualization of the cosmic microwave background or an awe-inspiring depiction of the early universe's inflationary period, these collaborative efforts continue to illuminate the profound and intricate story of our cosmic beginnings. Some of the most compelling visualizations of the universe's beginning have emerged from a rich collaboration between artists, scientists, and state-of-the-art technology. These visualizations, often created using data from cutting-edge telescopes and sophisticated computer simulations, bring the early cosmos to life with stunning clarity and detail. One remarkable example is the detailed renderings of the cosmic microwave background, CMB radiation. Produced from data collected by the Planck satellite, these visualizations reveal the universe as it was just 380,000 years after the Big Bang. The CMB maps are often color-coded to illustrate minute temperature differences, which correspond to density fluctuations in the early universe. These fluctuations eventually gave rise to galaxies and larger cosmic structures. The intricate patchwork of blues, reds, and greens on these maps provides a glimpse of the universe's primordial conditions, offering an almost tactile sense of its nascent complexity. Another enthralling visualization is the depiction of cosmic inflation, a rapid exponential expansion of space-time occurring a fraction of a second after the Big Bang. Animations of this phase can be particularly impactful, showing how an initially minuscule, extremely dense point expanded to form the vast cosmos we observe today. These animations often use expanding grids or ballooning spheres to convey the mind-boggling speed and scale of inflation, making an otherwise abstract concept more comprehensible. The formation of the first stars and galaxies, often termed as the cosmic dawn, is another captivating visualization. Simulations and animations illustrate how gravitational forces caused gas and dark matter to collapse into the first luminous objects. These visualizations frequently transition from the homogeneous early universe to a richly structured cosmos filled with clusters of galaxies and sprawling filaments of dark matter. Such depictions encapsulate billions of years of cosmic evolution in mere minutes, highlighting key processes that shaped the universe. Moreover, simulations of large-scale cosmic structure, such as the Millennium simulation, offer compelling visuals of how galaxies are distributed throughout the universe. These highly detailed simulations, run on powerful supercomputers, blend observations with theoretical models to recreate the web-like structure of the cosmos. They show galaxies arranged in vast filaments and clusters, interspersed with enormous voids, effectively rendering the cosmic web. Interactive visualizations like those available through virtual reality, VR experiences, and planetarium shows further enhance our engagement with these cosmological concepts. VR allows users to fly through the early universe, witness the birth of the first stars, and traverse the large-scale structure. Planetarium shows often combine narration with immersive 360-degree visuals to create an educational experience that is both captivating and informative. By transforming complex data and theoretical models into visually stunning representations, these visualizations not only aid scientific understanding, but also inspire a sense of wonder and curiosity about the origins of our universe. They bridge the gap between intricate scientific concepts and public perception, making the awe-inspiring story of the cosmos accessible to all. The origin of the universe has always fascinated inquisitive minds due to its profound implications about our very existence. My interest was sparked by the realization that everything we see around us, from the smallest particle to the largest galaxy, shares a common history that traces back billions of years. One cannot delve into the tapestry of cosmology without being awestruck by the concept that the universe began approximately 13.8 billion years ago with an event known as the Big Bang. This explosion set into motion a sequence of events so complex and intricate that it continues to baffle and inspire scientists and enthusiasts alike. What truly deepened my curiosity was the realization that each discovery is just a piece of a grander puzzle, unveiling a narrative written across the expanse of space and time. For instance, the cosmic microwave background radiation provides us with a snapshot of the universe when it was merely 380,000 years old, a period when temperatures were so high that atoms couldn't even form. This faint glow, detected as microwaves, is a whisper from the infant universe, echoing secrets of its nascent moments. From the birth of the first stars and galaxies to the eventual emergence of life on Earth, each chapter piques a desire to understand our own place in this vast cosmic story. My understanding of the universe's beginning has evolved in tandem with the field of cosmology itself, reflecting the leaps in knowledge and technology that have illuminated the shadows of our ignorance. Initially, my thoughts were dominated by the sheer magnitude and mystery of the Big Bang, an almost mystical event. As I delved deeper, the abstract concept began to crystallize through the lens of scientific evidence and theories meticulously pieced together by generations of astronomers, physicists, and cosmologists. The discovery of the cosmic microwave background radiation was a significant turning point for me, solidifying the Big Bang as more than a theoretical construct, but as a verifiable cornerstone of our cosmic history. What further enhanced my understanding was the introduction of advanced tools, such as the Hubble Space Telescope, and more recently, the James Webb Space Telescope. These instruments have allowed us to peer back in time, capturing the light from galaxies formed mere hundreds of millions of years after the Big Bang. The increasing precision of measurements, such as those of the universe's rate of expansion through the observation of supernova and the detailed mapping of the cosmic microwave background, have provided a clearer picture of cosmological inflation and dark energy. Each of these discoveries refines our conceptual framework, transforming the origin of the universe from a simple explosive event into an intricate ballet of physics, unveiling a dynamic and ever-evolving picture of our cosmic dawn. I hope viewers come away from this documentary with a profound sense of wonder and a deepened appreciation for the intricate tapestry of the cosmos. The universe, in all its vastness and complexity, can often seem incomprehensible, but through a careful and engaging exploration, I aim to make these grand ideas accessible and inspiring. I want viewers to grasp that our universe is not just a backdrop for our existence, but a dynamic and ever-changing entity that has evolved over billions of years. Understanding the origins of the universe opens our minds to the broader implications of our place within it, and can profoundly change our perspective on life and existence itself. Moreover, I hope this documentary ignites a curiosity and a passion for science and exploration. By showcasing the collaborative efforts of scientists across disciplines and elucidating the scientific methods used to unravel the universe's mysteries, viewers can appreciate the value of inquiry and evidence-based understanding. The journey from the Big Bang to the present day is a narrative rich with discovery, challenges, and breakthroughs. By bringing this story to light, I want viewers to not only be informed, but inspired to seek their own understanding and perhaps even contribute to this ongoing quest for knowledge. The cosmos is a story still being written, and there's a place for everyone in its exploration. Studying the origin of the universe has profoundly shifted my perspective on humanity's place in the cosmos. When you consider that all matter, including every atom in our bodies, originated from the remnants of ancient stars, it instills a sense of profound connectedness to the universe. This understanding reinforces the notion that we are not just isolated entities, but intrinsic parts of an ever-evolving cosmic tapestry that stretches back billions of years. By recognizing that the atoms in our bodies were forged in the hearts of dying stars, we can appreciate our existence as a continuation of the universe's grand narrative, linking us to the celestial processes that have shaped everything from the smallest particles to the largest galaxies. Moreover, this cosmic perspective emphasizes both the fragility and the uniqueness of life on Earth. The vastness and complexity of the cosmos highlight how extraordinary our planet is, providing the precise conditions necessary for life to flourish. This realization can foster a deeper appreciation for our shared existence and the need to safeguard our planet. It underscores the importance of scientific inquiry, collaboration, and stewardship of our environment. Studying the universe's origins not only expands our intellectual horizons, but also enriches our philosophical and ethical understanding, encouraging us to cherish our place in the cosmic expanse and responsibility towards each other and our planet. The next steps in my journey to understand the universe's origin involve diving deeper into both theoretical explorations and practical observations. On the theoretical front, keeping abreast of advancements in particle physics and quantum mechanics is essential. These fields offer insights into the conditions that prevailed in the earliest moments after the Big Bang, potentially unveiling the mysteries of cosmic inflation and the nature of the initial singularity. Engaging with the latest research papers and participating in scientific conferences allows for a continuous flow of new ideas and hypotheses to challenge and refine my understanding. In parallel, advancements in astronomical observations are pivotal. The James Webb Space Telescope, with its unprecedented infrared capabilities, is expected to uncover some of the earliest galaxies and possibly the first stars ever formed. By studying these ancient objects, we can piece together a more coherent narrative of the universe's infancy. Additionally, collaborating with astronomers and cosmologists, and even participating in citizen science projects, can provide first-hand exposure to cutting-edge discoveries. Engaging with initiatives like the Large Synoptic Survey Telescope (LSST) project promises to yield new data that could revolutionize our understanding of dark matter and dark energy, fundamental components shaping the cosmos. By harmonizing these theoretical and observational approaches and continuously fostering a curious and open-minded stance, I hope to contribute to and benefit from the ever-growing tapestry of cosmic knowledge. This journey is as much about the questions we uncover as it is about the answers we find, each step bringing us closer to understanding the profound mysteries of the universe.